the new evaluation of the last presentation also again. So that is null and void. Please don't get scared. Secondly, the topics that have been chosen are more or less graduate topics. To be very frank with you, I'm sure even many of the aerospace engineering colleges these days don't have the facility to deal with such topics. So you have come to Mecca and Medina of India, or maybe of the world itself, because agents used to be head of the department here, and you don't know whose agents. Discover it by yourself. So you are at the Mecca and Medina of knowledge, and this is the place where you can learn anything and everything about. Since the background knowledge was not there, probably assuming that it was not there with you, what has been decided by Prof is that one is that now, apart from the present one, you will still have 11 presentations. So in those 11 presentations, not only in terms of finding the information as to where can you find the information about what, or the discussions about the topic, or at the same time helping in presentation or giving guidance in presentation, we both TAs are available to you. You need not take precious time of Prof and punch him with bags. You have been doing that today for quite some time, and you know that the rebounds, bullets come back to us also. So we have written some of the bullets. So please punch us instead of punching him. That's what I would like to request. And as I said, we are quite open, not only in email, in the outside the class and in the class. So please ask us what you want, information or topic understanding, or what is it exactly. If we don't know, then we'll go back to Prof and we'll clarify it further. Okay. So information as well as help in guidance and presentation will be given to you. That's it I want to confirm. Thanks.
Can you please put that on?
Oh, sorry, sir. I think I'm okay, sir. That's what I wanted to say. Now, the first one, as I last time said, this is a thin plate. Most of you feel an aeroplane needs something to fly. It doesn't. Even a flat plate is okay to fly. And secondly, this is a slender aerospace structure as it is that you can see. When I dropped it, it tumbled like this, isn't it? So why did it tumble like this? And could you see the way in which it tumbled?
Switch it.
Please observe carefully. Yeah?
The top.
Yeah, I dropped it in the other way around. Can one of you switch off the fan, please? I think that is disturbing. No. It's pretty sensitive. In fact, we were told when we were in the Air Force not to step on the wing, because it's as sensitive as that. So don't step on the wing of an aircraft, okay? See what happens. Okay. Can you please tell me 2 things about it? At least 2 sentences. Any one of you, please. This is the paper. Here is the airflow. Here is your CG. And here is your aerodynamic center. Okay. And here is the lift acting, and MAC is acting. Right? Can you please tell me? So because of it, it is, tumbling this side. At the same time, when it starts tumbling, it has lost everything. It has become literally like a cylinder. Now it wants to gain back. Now it is only CG which is trying to push it down. Therefore, the rolling rate would decrease. Sure, isn't it? And thereafter, it will try to regain its position back in whichever stable condition it is. And then again goes back into the loop. So it's a classic case of tumbling of plates, which is a non-linear oscillation. That's how it is. So this is one thing which I wanted to bring about. Second is about the camber. He called it as dihedral, but at the same time it is camber. Now what I will do is, logically, since the moment is acting like this, I will reduce the moment in order to make it to fly. Last time I showed you like this also and like this also for you to realize. But then actually what I am doing is I want to reduce this moment. If I want to reduce it, what will happen? What should I do? Spoil the lift. So I should give a reverse camber. Sir has already brought out the spoilers. So I have reversed the camber. Now see what happens. So it has lost its initial rolling attitude and it is now doing a different thing since I have given a reverse camber. See, it's not rolling anymore, but it's still not doing its performance. Now that comes to today's topic. Performance can be understood in many ways. I don't know if you have thought of this before this class. Before putting that performance word, at least I thought of it 100 times. Each time I got different answers. Probably if I say landing runway, it's a performance. If I say maneuverability, it's a performance. If I say range, it's a performance. If I say the G that it pulls and maximum rate of turn it can do, it's a performance. Therefore, each one of you can pick up each performance and talk about 15 minutes about that only. Therefore, the topic is definitely valid, I feel, and it is wide enough scope for that matter. In this case, what I'm saying is the maximum range that it can fly through. In the first one, it tumbled and went on. Irrelevant for us. It went into an unstable mode, initially stable, unstable, and later on fluctuating between instability and stability. Now, if I reverse the camber, it is absolutely falling down with its own CG. It is no effect. Then I came out with, suppose I want to do some improvement to this, then only thing that I can do is, with this I have done maximum. I have already reversed the camber. There is nothing that I can do. I can shift the CG. So I did shift the CG, and the shifting of the CG depends on how much do you shift. So that is in my control. Then I'll have range, performance, or whatever. The last one, I don't know whether I used this or, see, now I have fixed I'll shift the CG a little more forward, make it a little more stiff. Wow, it reaches some destination at least. I think this is the last that I had last time. It tries to reach something, but you can try on your own by moving the CG forward or backward, depending on how much does it do. See, so it reached a little more distance. So basically what I wish to tell you is that the performance of range is something that is maneuvered or altered by the margin that you have created. Thanks. That's all I wanted to say today.
So you can go ahead. First team to present.
Good afternoon, everyone. We are Team Garuḍā, and topic for our today's presentation is Aerodynamic Center. We call it a phantom pivot. Why? We will explain it. Let me introduce our teammates: Abhishek sir, Kunal, Rohan, Ashish sir, Sanket, Nitin sir, Sricharan, and me myself, Kaustubh. So before that, let me give you an example. This is a fighter jet, as we all can see, and you can see that this fighter jet does not have a tail, or what we call as horizontal tail or empennage, but still it is stabilized because it flies. But we know that stability, for the stability purpose, horizontal tail is important. It gives us the pitch control, it gives us the longitudinal stability. So question arises, how does this aircraft still fly and still stable, even though it doesn't have any horizontal tail? And to answer that, we won't give a spoiler because the topic of our presentation, Aerodynamic Center, we manipulate it in order to give how we can control it. So let's get to more basic before we go toward how Aerodynamic Center works or what is Aerodynamic Center. First, we all know how aircraft fly. We spent our last presentation knowing what are the forces that act on an aircraft and what makes it fly, what gives us lift, what gives us thrust. But what maneuvers the aircraft is the movement that we give it to it. We give a roll, pitch, or yaw movement, so the aircraft fly as per our convenience. But sometimes the gust of a wind can give turbulence and give unwanted movement to that aircraft. And we don't want aircraft to follow those movements. We want a stability that can go against those movements. So when we want that stability, we want to calculate how those movements work. But unlike forces, movement need a point of reference in order to calculate them. And what options do we have? We have, let's say, two options. First is conveniently our leading edge. Second is conveniently a center of pressure. Center of pressure is a point at which the moment of center of pressure is zero. So we don't have to calculate one moment for once. But the problem with leading edge and center of pressure is that as we do our analysis, we find out that center of pressure vary as we change our angle of attack. As we increase our angle of attack, the center of pressure move forwards. As we can see, the XCP decrease, and this steep curve is actually a discontinuity. The programmer just attached these. So we want to calculate how. So we need a point which is not like this. If the center of pressure move with angle of attack, we have a hinge that is changing with time, and we cannot write a stability equation on those hinges. So we need something else, which is not leading edge, which is not a center of pressure. We need something about which the movement stay constant. And for our convenience, let's just say that point is called aerodynamic center. Although it is written, it is C/4, but we don't know where it is. So our convenience, the center, aerodynamic center is a point about which the movement is always constant irrespective of angle of attack. So how can we calculate the movement? Let's just say there is a leading edge and the movement across the leading edge is MLE. And at a particular point, let's just say XAC. AC is the distance of aerodynamic center from the leading edge. There is aerodynamic center. We apply lift to it. So what movement do we get? We get movement across aerodynamic center minus XAC into the lift that is applied. Now, our convenience, we only want MAC to stay constant when we differentiated it with alpha. So we want these terms to be 0. Now that is the basic of our further derivation, and that derivation will be explained by the Sri Charan.
So continuing forward, so now we want to calculate where the aerodynamic center actually exists. So let's assume this airfoil section. Let's say we'll take some reference point, that is C/4. Let's say the aerodynamic center does not exist at that point, just for assumption. So as the equation is written here, so if you just normalize it using non-dimensionalize it using let's say dynamic pressure, you will get in terms of moment coefficients. And this is the equation you get if you write moment coefficient around aerodynamic center for this configuration or for this condition. You can just do the math here. So here what we are doing is we are using thin airfoil theory to analyze the lift produced. What is the amount of lift produced by a thin airfoil? Either it might be a cambered airfoil or a symmetric airfoil. So this is from thin airfoil assumption. We will find CMLE is equals to pi alpha by 2. And so continuing the derivation. So if you differentiate with respect to alpha, so you will get this equation. And since we already defined aerodynamic center as a point about which your CM will not change with respect to angle of attack, you will get this as 0. So continuing. So when you write in terms of aerodynamic center, see if you have, we have aerodynamic center, location of aerodynamic center here, which is defined as XAC, this one. So if you write equations in terms of aerodynamic center, this M0 is nothing but CM about M0 is this quantity and A0 is this quantity. So if you write it down and do the interpolation, you will get something like this. So which is XAC is equals to minus of M0 by A0 plus 0.25. So this equation we will get it from thin airfoil theory. If you represent a whole airfoil as a thin sheet or a thin sheet of vortex, so this goes to circulation concept as well. So this M0, if you take it for a symmetric airfoil, you will get M0 as 0, meaning your aerodynamic center exactly lies at quarter chord of the quarter chord basically. But if you take a cambered airfoil, it will be around the quarter chord. So as I mentioned, so it will be around the quarter chord. If you do the calculation, let's say for the 5-digit 23012 airfoil, it will be around 0.24 the chord of the whole chord of the airfoil. So it's very close to 0.25. So we can effectively assume that our aerodynamic center lies at quarter chord of the airfoil. Yeah. The effects of airfoil on the performance, effect of aerodynamic center on the performance of the aircraft will be explained by Abhishek sir.
Good afternoon, sir. Now, after knowing the concept of aerodynamic center, our main goal is to see how aerodynamic center affects the performance of aircraft. Performance in terms of stability, in terms of maneuverability or efficiency or range. So right now I am going to present how it's affect the static stability of aircraft. And before going to static stability, just from our high school physics, we know that any system is said to be stable if it has a restoring force towards the point of equilibrium. So giving the classical example of ball and point, we have these three cases, either this or we can go for spring mass system also. Say in this case, if this ball is displaced from its equilibrium point to some another point, if we find out the forces acting on this, that is a normal and due to gravity ignoring other frictional forces, we see that always there is a component of gravity which acts to restore its position towards the equilibrium position. We call this system to be a stable system. This system, where if it is displaced from equilibrium point, it just goes to another point. We call that neutrally stable. And the third example, where if any disturbance is there, it just topples and will not return at any time towards the equilibrium position. We call that statically unstable system. Okay, for talking about the static stability, we only focus whether the restoring force is there or not to bring it to equilibrium point. We don't, in static stability, we don't worry about how it goes to the equilibrium point and in what time it goes. That will be discussed in when we discuss about dynamic stability. So coming to aircraft, there are two concepts, not two concepts, it's considering a wing, if aerodynamic center is behind the center of gravity, in that case, if any disturbance is there, the moment due to lift, it causes to the aircraft to go in static in equilibrium condition. And for wing, we define aerodynamic center, but when considering the entire vehicle, we consider neutral point. Okay, so the stability conditions are like if CG is ahead of neutral point, it's a stable configuration. If it is both point is at same, then it is neutrally stable. And if it is neutral point is before CG, it is unstable configuration. Okay, and mathematically we can say that if moment rate of change of moment with angle of attack, if it is a negative, then our system is statically stable. Okay, now coming to the stability, now we have understood that if AC is behind CG, it will be statically stable. But next question is how much it should be behind, because for everything there is cost associated with it. But so for general commercial vehicles, it's about 5 to 10% of mean aerodynamic chord, which is aircraft is behind that. So AC is behind, or neutral point is behind the CG. Okay, but is this criteria means universal criteria, or is it like always we have to make aircraft statically stable? The answer is no, because it comes with a cost of maneuverability. If a vehicle is more stable, it will be less agile. So wherever we need agility, like fighter aircrafts, okay, or in some cases missiles also. So there we need a opposite uh, position of AC to CG, that we call relaxed static stability. In this case also, it's about 1 to 5% of mean aerodynamic chord. But here the cost is cost associated with is high computation through the computers to keep it stable. Okay, and next it will be discussed by my colleagues.
Thank you. So I will be discussing about the effect of aerodynamic center to dynamic stability. So before that, we should have a clear concept about neutral point and CG and static margin. So here we can see, so in this figure, so we have aerodynamic center. So basically aerodynamic center is defined for the wing. So if we define aerodynamic center for the aircraft, so it is simply the neutral point. So neutral point is simply the aerodynamic center of the whole aircraft. So it will consider the aerodynamic effect of whole wing, fuselage, tail, and other components. So we can say that stability is free, and after AC requires the tail to generate negative lift to balance the nose down movement. This forced the main wing to work harder, creating a trim drag. So we have introduced a new term called trim drag. So now we can discuss about the effect of aerodynamic center on dynamic stability. So we have three cases. So first is positive static margin, another is zero margin boundary, and last one is negative static margin. So in first case, CG is ahead of NP. So that is, we simply called it as positive margin. So in this case, our aircraft is statically and dynamically stable, and modes are well damped in this case. And simply we can found this kind of stability in standard transport aircraft. And we have another zero margin boundary. So zero boundary is simply in this case, so CG and NP coincide at the same point, and there is no any restoring movement, and aircraft stays where it is put. And in this case, we need active stability augmentation. So active stability augmentation is simply a control system based method which is used to improve and maintain the aircraft stability. So last one is negative static margin. So in this case, our CG is behind the NP. So now we simply called it as negative static margin, and we can see that in this case oscillation grow exponentially. So that is, in this case, our aircraft is unstable, and this kind of stability requires fly-by-wire. So this is the dynamic response of the aircraft. So while doing the dynamic stability test of the aircraft, we perform different dynamic tests. So first one is short period oscillation, another is Phugoid oscillation, and two more. We can also perform Dutch roll, and one we can also perform spiral mode. So I explain only the short period oscillation and Phugoid oscillation. So in if our aircraft have positive starting margin, then we get the short period oscillation, like we can see this in this graph. So a fast high frequency oscillation of the angle of attack, strongly affected by CG and P distance, a large starting margin results in heavier damping. Similarly, we have Phugoid motion. So here we have low frequency trade-off between altitude and airspeed, and damping is naturally weak and reduced further as starting margin decreases. So if you conclude all this, we can say that short period is a variation in incident where the air hits the wing, while Phugoid is a variation in total energy, that is airspeed versus altitude. So now I like to invite Hébbāl.
Myself, Nitin Jaiswal. As of now, we have discussed the different cases of static margin, being positive, negative, or zero, defining the stability of the aircraft. Now I'll be discussing about the different configurations that are there which utilizes this concept of static margin to suit their own requirements. First of all, if we talk about a conventional configuration with an aft tail, the major requirement is the comfort and the safety of the passengers. Thereby, it requires the aircraft to be stable. So in that case, we tend to have a positive static margin, and that is helped by the presence of the aft tail, which is there in the aft of the aircraft, thereby shifting the CG, shifting the neutral point aft, and giving us positive static margin. Secondly, if we talk about a fighter aircraft, which typically utilizes a delta configuration, the neutral point is basically forward in that case, and CG is aft, thereby giving a negative static margin. And that is a requirement for such aircraft because we need high maneuverability and high agility. And the third case is of a flying wing configuration, which is basically a tailless configuration without any vertical tail and a horizontal tail. Now, in this case, what happens is that because of the geometry, which is triangular for such aircraft, the CG naturally shifts aft. But the requirement is that we have to keep such aircraft statically stable in the longitudinal directions. So the only way is that we can shift the CG forward and ahead of the neutral point, because there is no such vertical tail or horizontal tail to keep it longitudinally stable. So in that case, although these such kind of configurations are inherently unstable, but they are enforced to be stable by putting a positive static margin, and they are basically used in UAVs and UCAVs. Next, Sanket will follow.
Hello sir, my name is Sanket, and I will tell you about that how performance changes by engine placement effect. Basically here we have shown three engine configuration: underwing, tail mounted, and flying wing. First, the underwing engine configuration. This is the most common type of configuration which we see in all the airliners. Here, because the engine is mounted below our wing, the CG is a bit forward, and also the drag induced by engine plus the wing is actually lower than drag which is induced by engine and wing combined separately. Why is this happening? Because first the wing is there in suppose undisturbed streamlines. The wing will first disturb the streamline, and if we consider the engine again, the engine is lying in the disturbed streamline, because of which the net disturbance is actually lower than what we consider for individual disturbances. Hence, the drag induced is actually a bit lower, which is which increases our performance a bit. But there is a problem with this also. The engine, when mounted on the on our wings, actually creates a nose down effect. To cancel that nose down effect, we use the concept of tail, and which help us to which is used to trim the pitch. In this case, the tail actually creates a lift upward. But since the area of the tail is much smaller than that of the wing, the lift created is a bit smaller. But because it is lying such a large distance from the wing, the moment arm of it is more, because of which the moment induced is able to trim the pitch, and hence we can get a level flight with it. But there is a problem with this effect. First, because we are adding a tail, the weight is increasing, and hence after the engine, at the exhaust, there is the wake region where the flow is turbulent inherently. Because of which, if we keep the tail near the wing, near our wing or the engine, it won't perform effectively. Hence, we have to keep it a bit away. Because of which, the CG is again shifting behind, and hence my stability margin is decreasing. And also because over the wing, the flow is taking place. Hence, the skin friction is again going to increase, which causes the performance to decrease a bit. Second, we might think like, why not mount the tail? Why not mount the engine on the tail? This is actually done in case of private jets, as case in the Dassault Falcon series. The main advantage of this is that because the engine is much behind the cabin is much noise free, which is mostly preferred by all the private jet owners. But there is a problem in this. Engine is a heavy component, and because of which the CG shifts behind. Hence, my stability is going to decrease because the distance between CG and neutral point is decreasing. Secondly, now my engine is either in front of the tail or just above the tail. Now, as I said before, there is a wake region. So my default tail configuration can't be used. Hence, here we use the configuration like T-tail or a V-tail, which performs both the pitch up, down and sideward motions. But controlling of this effect is also a computationally challenging problem. Now, what we can do else is that, what if we remove the tail completely, which you rise to the flying wing configuration. In case of flying wing configuration, the complete body of the aircraft is a flying wing itself. Here, the engine is mounted inside the wing only, because of which the motion of streamline is smoother enough that there are no wake regions, because of which the performance is much better. On the research paper which we studied, it was found out that it is 50 to 20% much better performing, or it has 50 to 20% more efficiency than a normal airliner. But the problem is that this type of aircrafts are actually unstable in nature. To make them stable, specific aerofoil shapes and computer programs have to be used. This is the reason that it is mostly now for military purpose only. Next, I will like to call Rohan for.
Good afternoon. My name is Rohan. Now I will be explaining about application. Basically, in fighter jets, we require agility. So therefore, there is 0 to negative static margin. And then in transport aircraft, we have high static margin, which prioritizes passengers' safety. Now, this safety costs us a lot. Now it introduces our trim track. Now, as you can see in this case, when AC aerodynamic center is behind CG, there is a nose-down movement. To stabilize the aircraft, the tail has to produce nose-up motion. So it can do it by deflecting and control surface. So due to which the drag is introduced, drag increases. And now due to this drag, there is effect in range. As you can see, the range is inversely proportional to drag. Now as drag increases, range decreases. So that's why for bombers and long range aircrafts, we generally prefer CG to be close to the neutral point. As you can also see from the graph, like from aircraft range versus static margin, for commercial zone, we have 5 to 10% of static margin, and for long ranges, we have around 2%. Now I will get. Okay. Now let's see how it can be achieved. For example, in transport and cargo aircraft, basically the cargo is kept close to the tail so that the CG is moved towards the neutral point, which allows for stability and reduces drag, which saves us thousands of dollars of fuel as per flight. Now, that's why we say that there is a great trade-off between the safety and economy. There is also a saying that free lunch in aerospace engineering. There is no free lunch in aerospace engineering. Every Newton of stability is purchased with the currency of drag. So when we go for safety, there is a drag, but when we go for economy, there is a high long range and fuel efficient, and it can also be seen as maneuverability. Now, Ashish.
Good afternoon, everyone. Myself, Ashish Raman. So let me take you back to history. The year is 1941, and this is a P-38 Lockheed aircraft. This is a fighter aircraft, and it used to nose dive. And then basically the modus of operandi, like it is a fighter aircraft, it nose dives, and then when it is at high speeds, what they found out that the control stick is not working. The pilot found out, even as mentioned by the Colonel Signa Gilkey, it felt like the stick was set in concrete. So the pilots thought maybe the stall has occurred. The engineers thought maybe the elevator cables which are there, they might have broken, but actually both were wrong. And till now, you have heard that the aerodynamic center is placed at the quarter chord. Everyone says that. So is it true, like across all the flight conditions? Yeah. So it is not. And the answer for the earlier incident was the Mech shift, which we call. So what happens, whatever my friend Shri mentioned, that the aerodynamic center is placed at the quarter chord is valid only for the subsonic conditions. Once it reaches the supersonic conditions, the aerodynamic center actually shifts to the 0.5, the half. So now this presents a terrifying problem. See, at that time, and as you might have noticed, our heading for the title for our presentation was the phantom pivot. Why phantom? Is because you cannot measure it like on the ground. Like CG, everyone, you can place on aircraft on the load cells, you can measure the CG. But what about the aerodynamic center? You can't measure it on the ground. And it changes. That is the most terrifying part when you are flying. So you have to design your engineering solution in the ground, keeping for all the conditions that the aircraft might encounter during its flying. So this is the Concorde aircraft. And we all know it was one of a kind supersonic commercial aircraft that was used at that time. And the same problem, the engineers now knew that the aerodynamic center moves back. So what problem does it causes? As it has been told till now, static margin is there between the neutral point and the aerodynamic center, the distance, and it determines the stability of the aircraft. Stability in turn determines how much your performance of the aircraft will be, because the trim drag comes into the factor. So if you suppose your CG is here, aerodynamic center is, for it to be stable, it will be placed at the back rear of the CG. So suppose during the supersonic, when the aircraft is going into the supersonic speed, the aircraft shifts back. The aerodynamic center shifts back. The static margin increases. Now the nose down moment of the aircraft is too much, and for that, to counter that nose down movement, the tail has to produce a negative lift. As you will be knowing, as my friend Rohan also mentioned, the trim drag. So I will not go into that in detail. So how do you resolve the static? How do you maintain the static margin? So what the engineers at that time ingeniously thought was, why not use the fuel tank? The fuel is there, that has a lot of weight. Why not shift it back and change your center of gravity? In this way, you will be able to, as mentioned in the title, chasing the ghost. So you are basically moving the CG aft as your aerodynamic center goes back. Another was the F-14 Top Gun. I think everyone has seen Top Gun movie. So you would have seen the wings, they can go back. It's why this was done was the same reason here, was the fact that if you want to catch the aerodynamic center,
So by sweeping the wings back, you change the CG distribution. But this was very costly in terms of like the weight penalty it induced, because there has to be a pivot mechanism. And at that time, this was made of titanium. So this was costly. So then what is the modern solution? The modern solution is relaxed static stability. And what it does is basically we are designing for an unstable aircraft. Why unstable aircraft? Because if it is unstable, your aerodynamic center is in the front of the center of gravity. And the interesting thing, so now what happens? This is a fighter aircraft. It goes into supersonic speeds. The aerodynamic center shifts back. It becomes stable. So you will go from instability to stability. And that's the beauty of this. So why didn't we use this relaxed static stability in the Concorde? Because at that time, the fly-by-wire computers, they perform calculations 40 times per second. And during that time, it was not proven that much. So that's why we didn't use this fly-by-wire system that time. So to conclude, aerodynamic center, so we have the performance triangle, the stability, efficiency, agility, and the aerodynamic center is the fulcrum point based on which you can decide whether you want the efficiency or you want stability or agility. Thank you.
Audience can ask questions first. So many of the subtopics are very closely related, so you will see a little bit of overlap. So I'm sure you guys should have some questions or the other.
Yes, any question?
There is an alternative. Yeah. Each question carries either a chocolate or a marks. Can I? One of you brought out that aerodynamic center shifts to 50% of chord in. No, there is no need of slide. While it goes to supersonic, definitely. In subsonic regime itself, is MAC constant? Aerodynamic center, is it constant subsonic? Is it, first of all, how did you come to aerodynamic center itself? Did you work out? I mean, sorry, you did that mathematics just from the fundamental physics. Do you realize something, which is, if you just put an aerofoil and put the pressure profile, can you realize what you're looking at?
No, sir, we can only see center of pressure and center of gravity of the aircraft. But when we did the calculations, so for symmetric airfoil, when we use thin airfoil theory and do the calculation, we found that the moment about center of pressure lies at quarter chord, and moment about it is zero, and it remains constant for different angles of attack for symmetric airfoil and thin airfoil theory. Then we realized that okay, there might be some point which has this characteristics where the CMAC with respect to angle of attack remains constant. So when we extrapolate it to the, let's say, general cambered airfoil, so and same when you use a thin airfoil theory, it was found that it has some relation and it remains constant.
But I understood this.
Yeah,
it was a very fundamental. I mean, not to go into this calculation at all. Just putting one profile on top, looking at it physically. Can you just in one sentence tell me how did you arrive at aerodynamics?
Yes, sir. If you see pressure distribution, sir, as we go away, pressure distribution comes down. So moment is nothing but product of force as well as moment.
It's a moment balance.
So,
Yeah. So by looking at it itself, there is a moment shift. A moment would lift. I mean, force can act, but moment can shift. It is that. That's one. Some of you mentioned aerodynamic center for the wing. What about aircraft?
So that is
It's a tail contribution you should consider.
Yeah.
Most of you, I think, so okay. What do you mean by stability? I think answer is. What do you mean by stability?
As told, sir, stability means if there is any disturbance to equilibrium point, there should be some restoring force. That's it. Yeah.
So stability kind of sense what is stability.
So if it has, so basically stability is if it has a tendency to come back to its equilibrium position.
What is no? I am not asking.
So if it is a trimmed aircraft, let's say trimmed at 4-degree angle of attack, there is some gust which disturbs it, which increases the angle of attack. Then there should be enough restoring force, or there should be restoring force which brings back that same trimmed angle of attack, trimmed position.
Let's say the aircraft is stalled.
Okay. Stall, then we have to use control system to recover. Yeah.
We can't.
Aircraft is stalled.
Yeah.
No define stability.
So in stall case we cannot define control.
So nothing else. You can. Aircraft is stalled. That's my answer. Wait, new stuff. In normal pilot's practice, he gets stalled and he comes back. That is first lesson if I'm right. Nose down attitude is called stable attitude.
Actually, the aerodynamic center.
Nose down attitude is called a stable attitude because once it's stalled, there is nothing that is happening. Slowly, it has to come down to the nose down attitude. The flow has to get reattached and re-established, and then you can. So basically, first thing is nose down attitude. Then our just wanted you to know. Yeah, thanks. It's not fighter or trainer or anything. Nose down attitude.
Thank you.
But well presented. Thank you.
Good afternoon, everyone. I am Garuḍā. So we will be presenting today static stability, and I think the previous team has covered that part very nicely and efficiently. But still, we'll try to make some justice to the static stability in the context of aircraft. And first of all, as Sir pointed out, what stability really means. So to have some intuition about stability, it is basically how much the system is resistant to a particular state in which it is right now. I mean, present. For example, if a system has a lot of resistance to leave its actual position, actual configuration at a given point of time, we say the system is highly stable. But there are different ways to look into that stability. And so there will be an analogy right now which I'll be presenting, which is an analogy of a spring mass system, and how really static, and why it is called static stability in the first place, because the system which we have taken for explaining the stability is in the static condition. So nothing is evolving with time. So everything is constant with time, no motion, nothing. So if you give a slight perturbation or disturbance, so we are only looking at the initial tendency, as has been pointed out. It is the initial tendency which actually tells whether the system is stable or not. I mean, for example, if the system is really stable, if you give an initial perturbation, the system will try to come back to its initial stable configuration. So that is only the static stability is all about. I mean, what is the tendency, or what is the initial response? The initial response when it is disturbed from its static equilibrium condition. So this is the analogy. And in terms of aircraft, how this correspondence is taking place. So this is the physical stiffness. So more is the stiffness, more is the restoring force, and you get more. I mean, the fight to come back to its static equilibrium position is much more stronger. So the same context in aircraft is basically all these control surfaces and all these wings, fuselage, everything combined, how they are able to generate the pitching moment, as Sir pointed out, to give a nose down attitude. So that is the analogy between a spring and a aircraft. And to give some idea about the stability, we have different kinds of stability. I mean, based on the initial tendency, one can have a nose down moment when you perturb. So that is a statically stable system. A system might be there in which any perturbation will actually tend to diverge. It won't be able to come back. Its tendency is go back from equilibrium position, and that is called an statically unstable system. And system, if it stays at the position where it has been perturbed, that is a neutral equilibrium position and neutrally stable system. And as we can see, just to give some mathematical idea, the physical stiffness what has been used to explain the spring mass system Here it is just the distance between the CG, and it has been pointed out very beautifully how the CG and how these aircrafts, I mean the aerodynamic centers play a very pivotal role in deciding the stability in the static stability case, of course. So that is how, I mean, we can use our different control surfaces and different design strategies and solutions to make effectively utilize our stability concept. For example, many fighters use the relaxed stability concept, in which in the subsonic cases the aircraft center, I mean the aerodynamic center is in front of the CG. And more on to this, our teammates will follow from here. So I'd like to call Somik and Adarsh to continue from here.
Good afternoon, everyone. Myself, Adarsh. The previous group told us about aerodynamic center, so I won't waste the time on discussing it. But I'll cover the main line that moment about the aerodynamic centers don't depend on angle of attack. It is always constant throughout. Now we'll discuss what are the conditions for the aircraft to be stable. So before that, first look at the two graphs. From the first graph, there are two airplanes pitching moment curve. The airplane one have negative slope and airplane two have positive slope. So B is the equilibrium point, trim point around which level flight is happening. Now consider if an upward gust is at the front of the aircraft, it will tend to increase the angle of attack of the aircraft. So if we follow the curve of airplane 2, the angle of attack will further increase, which is not stable. But if we follow the airplane 1, the angle of attack will decrease. Now the similar, if a downward gust approaches the aircraft from the front, then angle of attack will decrease, and for that airplane 2 is also stable. It will tend to increase the angle of attack. So we can see the negative slope results in more stable. And second graph, from in the second graph there are also two airplanes pitching moment curve, but as we can see both have negative slope. So but differences, one have negative intercept, one have positive intercept at y-axis. From the result of first graph we can say that both are stable, but it is not true, as the trim point, the point at which moment is zero, must lie at a positive angle of attack, because at positive angle of attack when level flight is happening, the lift is sufficient. So two conditions are necessary for stability to happen. First is negative slope and second is positive intercept. Now we'll talk about the wing contribution in the pitching moment. The figure then on the right hand side is a representative sketch. As you can see, the airfoil is replaced by a wing mean chord length, and the CG of aircraft is there. So if we take sum of all moments about the CG of aircraft, we'll get this first equation. Now dividing the first equation by half rho v square SC bar, we'll convert it into a lift coefficient or moment coefficient form. So we'll get this equation, and now we'll take small angle assumption, so that cos alpha wing minus I wing is equal to 1, and sine of any angle, small angle, is equal to that angle, and we'll assume that CL is very greater than CD. So we'll get this equation. Now we can put this CLW is equal to y is equal to mx plus c form that we know in place of that. So we'll get a equation where we'll get a CM equation, and if we break the CM equation in the form of y is equal to mx plus c, this is the slope part of final pitching moment equation due to wing contribution, and this is the intercept part. Now I'll let Somik cover the next point.
Good afternoon, everyone. So continuing from here, generally the values of CM0W and CM alpha W is positive, but as others said earlier, we need a negative slope for static stability. and now so we need a horizontal tail to counter that value and get the CM0 for the entire aircraft to be positive and the slope to be negative. Now we have in a similar fashion we have considered the moment about the CG of the airplane, and we have and after taking the equations and considering the general form of the moment coefficient value CM0 of tail plus CM alpha tail into alpha, we have the values as CM0t and the CM alpha t values as given here. And for references, all these parameters are given here. Alpha t is the tail angle of attack, alpha w is the wing angle of attack, IW is the wing incidence angle, IT is the tail incidence angle, and epsilon is the downwash angle. The downwash angle representation is also given here. Here we have the VH as the horizontal tail volume ratio, and all this. And then considering the total contribution from wing, tail, and fuselage, we have the equations in that form, and the values are also given CM0 and CM alpha. Now the CM0 value here we have obtained comes out to be positive. This is because of the tail contribution. From the wing contribution, the value generally is negative here. But for pitching, for trimming the aircraft at a positive angle of attack, we have added the tail to make the CM0 value to be positive, and the CM alpha value is negative also here to consider for the static stability line. So now we come to a concept called neutral point. The neutral point is the condition about which the pitching moment coefficient is slope is 0. So we considered the CM alpha values from this equation and equate it to 0, which gives the value of the CG location as XNP, or the neutral point. Now for static stability, we generally need the neutral point ahead of the airplane CG, and static margin is defined as XNP minus XCG by C bar. And from the next expression, we have CMCG alpha, or the slope of the CMCG curve as the minus of CL alpha into XNP minus XCG by C bar. Now CL alpha, as we know from the lift curve, it is always positive in the domain before stall. So this value comes out to be negative as required as needed for the static stability. And for and also the XNP minus XCG should be greater than 0 for keeping a stable aircraft, as said by our previous group, that static margin should be positive, or the CG should be ahead of the neutral point. Now for longitudinal static stability, one more point is the engine contribution, but which is not very well studied. So we have just given the points and not the mathematical representation of this. Now the engines are generally placed below the wings, which gives a pitching up moment to the airplane around the CG. And then also there are slipstream and jet induced airflow, which distorts the airflow around the tail. And we also have the mass placement of the engine, which alters the inertia of the airplane. And all these stability margins and all stability parameters gives rise to some affects the airplane performance, which are given here. Higher longitudinal stability increases the trim drag, because the tail must produce more force and to pitch the airplane up during and to make the CM0 positive. Then strong stability makes the airplane less maneuverable, as our previous group already said. Then we have the longitudinal stability slows the aircraft response, because if it is more stable, then we can't change its orientation from one to the other very easily. And so we generally keep we generally optimize or keep the longitudinal stability parameters reduced to improve the performance as a whole. From there, my teammate Shubham will continue.
So, hello everyone, I'm Shubham, and I'm going to explain about the directional stability. So, now let's suppose this is an aircraft. If a positive beta gust comes from the right, it's taken as positive sign, and another positive convention is the starboard side wing goes backwards. Okay, so if there is any yaw disturbance in the aircraft, and if it tends to come back to the equilibrium position, then the aircraft is said to be directionally stable. Now coming to this slide, the yaw moment coefficient. Actually, there is a mistake. The origin should be at the intersection of the lines. What happens is, actually we saw that for aircraft, suppose this is the aircraft, and if this is a positive beta angle, okay, so we need a yaw moment, positive yaw moment, that is this going to the back side. Okay, so for positive beta we need positive yaw moment or the positive yaw moment coefficient, Cn. So from here, and similarly for negative beta we will need negative Cn. So the plot should be like this. This is for stable aircraft and this will be for unstable aircraft. Okay, now looking at the yaw moment contribution of the various components. First one is the fuselage contribution. Actually, the fuselage is the yaw moment stability contribution of fuselage is destabilizing, and we get it from the empirical relation. Here Kn and KRL are the empirical factors, and SF denotes the projected area of fuselage, LF is the length of the fuselage, and SW is the wingspan area, and B is the wingspan. Next, coming to the vertical tail contribution. Again, we know that the fuselage is destabilizing, so vertical tail must be stabilizing to also counter the fuselage contribution. So for this we can see it is a minus eta into the tail volume ratio into Cy beta into beta plus sigma. Here the tail volume ratio is also a design parameter, which is a deciding factor for the tail contribution towards the net yaw moment. And overall this whole Cn will be positive, because here the Cy beta is negative. We can see from here, if again from positive, taking this example, in the positive yaw disturbance, the force that will be generated here will be in this side, and the reference coordinate axis we take is here in the y direction, here is the x direction, and downwards is the z direction. So we can see this is negative direction. So here from here we came to know that Cy beta is negative, so overall Cn is becoming positive, so the vertical tail contribution is stabilizing, and sigma is the side wash angle. Finally, coming to the wing contribution, first let us understand how the wing contributes to drag. Suppose this is my wing, okay, and this is taken as a sweep angle. This is known as a sweep angle. Suppose, again considering the case in positive beta yaw disturbance, V. On this side, the velocity will be V into cos of, sorry, this is not beta, this is lambda minus beta, and here the velocity will be V cos lambda plus beta. From this velocity difference we can see this velocity is more, so for a positive yaw disturbance, we will get a positive yaw moment. So the drag is also marginally stabilizing, contributing to the directional stability. And from here on, I'd call Nirav to explain further.
Good afternoon, everyone. My name is Nirav, and till now we have been talking about static stability, which is sort of an inherent phenomenon in an aircraft. I'm here to talk about more about directional control specifically. So control is something that pilots control using the directional control specifically, which is controlled by a pilot using the rudder pedal, by which it deflects the rudder, which is to change the effective camber of the vertical tail in order to provide some extra yaw moment in order to maneuverable situations like crosswind landings, where the aircraft tends to go in the aircraft nose tends to go in the direction of wind, but during a crosswind landing we need the aircraft nose to be aligned with the runway direction. So in order to accomplish that, the pilot uses the rudder in order to create a opposite yaw moment direction, so to control the aircraft basically. So the rudder moment is calculated by this formula, which is nothing but easily visualizable, as the rudder creates a lift component which is in an aircraft like this. The lift component is like this, or maybe like this, depending on the situation and the wind direction. And by multiplying the tail area to the moment arm to the dynamic pressure and the coefficient, we can calculate the effective yawing moment which we can apply with using the rudder. So this is all simple mathematics and stuff. So in order to kind of wrap this up to stability and control and all these effects, what does this actually affect? How does this actually affect the aircraft performance specifically? So in general, when we think about stability, we think that the more stable the aircraft, the better performance we will get, or the efficient performance we will get, which is sort of true in case of a multi-engine aircraft, where if by unfortunately an engine fails, so then directional stability plays a crucial role in order to align the aircraft and keep the aircraft in a particular attitude. But this is not true generally, because the stronger stability leads to more control requirement, or more rudder deflection during a crosswind landing, during any maneuver. Example, crosswind landing, where crab and side slip phenomenon require more rudder control when the aircraft is more stable. And then the last performance, a major performance issue comes with the interrelation of the lateral stability and directional stability, which my fellow cadet will talk about in detail later. But just to give a sort of physical intuition, what happens is that during a slight gust in yaw moment in your direction, the lift in roll direction, due to slight gust in roll direction, the lift component also changes its direction, due to which the slight slip is induced due to the lift also. So both the rolling and yawing motions kind of happen at the same time, which are in perpendicular planes, or which sort of correlates to each other. And so then it matters very much how strongly laterally stable the aircraft and as well as directionally stable the aircraft is. But if these are in out of phase with each other, it can lead to several phenomenon, mostly like spiral instability, where the directionally the aircraft is stronger than lateral stability, and it can lead to a Dutch roll kind of situation, where the directional stability is weaker than the lateral stability relative to the lateral stability. So these two need to be in phase, which we will talk about later in detail. So this was all about directional stability and all stuff. Next, my fellow cadet Gaurav will talk about roll stability.
So here I'll be talking about roll stability. So when an aircraft rolls, so basically because of positive bank angle, there will be a horizontal component of lift, and because of the horizontal component of the lift, there will be a side slip. So here is a front view of an aircraft. So for positive bank angle, so there is a horizontal component of lift along this wing direction, and there is a positive side slip angle beta. And if the aircraft is able to produce a restoring rolling movement in anti-clockwise direction, so the aircraft can get back to its original orientation. So from there we can say that the aircraft is stable in roll. So the requirement for roll stability is restoring rolling movement coefficient should be negative. And also the lift vector is getting divided into two components. So the vertical component is not able to balance the weight. So because of this, there is a decrement in altitude, and if the aircraft is stable in roll, so the restoring roll movement will bring back the aircraft to its original orientation and as well as to its original wing level altitude. So this is how the roll stability actually helps to maintain wing level flight. So now I'll be talking about the dihedral effect. So there is a front view of an aircraft. So because of positive bank angle, there will be a positive side slip, and if the wing is having a dihedral angle, so there will be a velocity due to side slip also. And because of the dihedral angle, we can divide the side slip velocity into two components. So one is along the bottom surface of the wing, and another one is normal to the bottom surface of the wing. So because of the normal component of side slip velocity, there will be a increment in angle. There will be change in angle of attack, and that can be given by normal component of side slip velocity by forward velocity. And also from trigonometry, we can say that the normal component of side slip velocity can be written as side slip velocity into gamma. And also we know that side slip angle beta is side slip velocity by forward velocity. And if we look at wing section 1, so with respect to air medium, the normal component of side slip velocity is acting in downward direction. So because of that, there will be an increment in angle of attack, and that can be written as beta into gamma. And if we look at wing section 2, so with respect to air medium, the normal component of side slip velocity is acting in upward direction. So because of that, there will be a decrement in angle of attack. So that can be written as minus beta into gamma. So at wing section 1, there will be a increment in lift, and the lift will decrease at wing section 2. So this will create a restoring rolling movement in anti-clockwise direction, and which will bring back the aircraft to its original orientation. So this is how dihedral effect ensures the roll stability. And the next part, fuselage contribution and sweep angle contribution, will be represented by Bharat.
Good afternoon, everyone. My name is Bharat Kumaris, and I'm talking about the fuselage contribution and or wing configuration contribution for the stability of aircraft. And there are three different configurations for the wing placement on a fuselage. Those are high wing, low wing, and also there is a mid wing. Mid wing is usually neutrally stable, but high wing is provides good stability, because when you can see the high wing is placed on the fuselage, when there is a wind component coming from the right side, it fuselage will block that wind on below of the right wing, and there will be a high pressure region on below the right side wing and low pressure region on left wing. This creates the restoring movement towards the equilibrium position of the aircraft, but it is quite opposite in the low wing configuration, because the wing is below and the same pressure is at the right side and low pressure at the left side. It will even destabilize the wing. So how much this stability is contributing from the high wing and low wing configuration can be given by that equation that shows like the contributing parameters are a distance from the central line of the fuselage and the horizontal line of the wing, and also the radius of the fuselage, which is which also tells how much pressure will build up at below the wings. And also aspect ratio and wingspan are the parameters which are contributing for the stability of this this configuration of the wing stability. And wing sweep, this is a backward sweep angle for the aircraft, and also here also where the wind is coming from the little bit offset right side, this creates more normal to the right wing of the aircraft, where you can see the more normal component of the wind is blowing perpendicular to the wing, which provides more lift on the right wing, whereas in the left wing this is more wind coming in a slant angle, which decreases the normal component of the component of the wing. So this is this decreases the lift on left wing and increases the lift on right wing. Again, it restores the rolling destabilization to the equilibrium position, and that was also given by the equation the parameters which are contributing for this sweep angle stabilization or like wing sweep angle, aspect ratio, and lift coefficient of the wing. Yeah. From H will continue from here.
Yeah, so everyone is already covered everything. So I will start with the stability is like a life. There are the days where you love the person. There are the days where you hate the person. So I will start with the hate and convert to love. So starting with the longitudinal stability, the first is the stability versus maneuverability. Everyone is already know that dCm by d alpha should be a negative and the same alpha should be positive. But the main reason is because we have to fly at a positive trim alpha angle. So we have to start with convert the dCm by d alpha to negative. So this configuration will be covered by the your wing and tail position. Plus you required a positive Cm naught because if we intersect backward to the y-axis, so that also will be done by your tail initial moment. Second is the CG range, which is already covered by previous group. That the main role is the static margin. If you have a higher static margin, your aircraft is more stable, or you have a lesser static margin, you have a less stability. But as we know that the CG is too far ahead of the nose point, the forward to the neutral point, already it's created that much nose down moment. While if you want to take off, the elevator doesn't have that much angle, or it does not produce that much moment to take off the aircraft. So we have to this all should be it should be a part of designing while we how to place our CG, how to place our neutral point, how to place our aerodynamic center from a wing, from a tail, from a air fuselage, and the overall aerodynamic center is called the neutral point. Yeah. So the trim drag is we already know that as we see that if there is some gust, upper gust, so that the physically it will create a nose up movement because my aerodynamic center is ahead of the CG, but the tail will counter at that same time. But the other thing is we have to also maintain the level flat, so we have to increase the more lift at the wing. How we will increase the wing? Just by accelerating our aircraft, but which will also induce the drag because the L is the drag is already proportional to L square. The fourth point is the control authority at a low speed. As we can see from the formula that as we have a low speed, that will not convert that much moment by aileron at a time of a takeoff. So we also have to incorporate that while designing our the horizontal tail, that we should select the that much volume ratio, and we have to place at a F part that it will create a sufficient moment. The E part is the ground effect. This is this already covered by Nirav, but the main thing is when the aircraft is while aircraft is landing, it's already have a nose down moment. So at that time the longitudinal stability already decreased. That's why the pilot have a easiness to easily maneuver at a time of a landing. If it doesn't happen, it should have a hard landing. Hard landing will happen. Yeah, Mark Tuck is already covered. So the main reason is due to the shock, the center of pressure is shifted behind. So it's already decreases the XNP by the static margin part, because this is as the sudden stability is increased, because our aircraft is designed for a nose down pitching moment. It's already it's already tried to nose down, and at that time my aileron doesn't have that much sufficient power to counteract that nose down moment. The second is the stall spin barrier. We also know that Lagrange stability, the one part is the dCm by d alpha. As we know that only the linear part is for a small angle. As at a high angle, it is not to be a linear; it's become a non-linear. So what we can do at a time of airfoil direction, we have to see that how much turbulence it will occur at a time of a stall. If there are so much turbulence which already blanket the tail, so that doesn't have that much energy to restore our aircraft. So it already have a loss of aircraft itself and the pilot which is flying. So this should also be your design parameter. The last is the fuel burn and the CG migration. So as we have seen at the Canard example, that by actively transferring the fuel towards the left, we can shift the CGs such that we don't have we are in the range of the static margin. For a roll stability, the very famous phenomenon is called the Dutch roll. So what will happen in a Dutch roll, where if this is the aircraft, and at a time of if you consider it's have a higher roll stability, so if the gust is here, then it will try to rotate in the similar fashion way. So this part will create a more lift. Because it create a more lift, it also increase a more drag, because we know that d it's proportional to L square. So the drag will contribute to the moment, and it's by nature it will shift to the right side. So at that time our rudder has that much power to restore that moment. Same with the adverse yaw. If we take the same example with the yaw, then the similar effect will be happen. And the last is the control reversibility. So as we know, there is not like a rigid structure in an aircraft. So at a high speed, it's have a tendency for a flexibility, but due to its have a flexibility of the wing, there is a inbuilt moment will be created by the wing, which will create a local change in angle of attack, which will also affect in a roll stability. So the last part is the directional stability, the spiral divergence. In the spiral divergence, due to the lower roll stability, whenever the gust will hit, it's already tend to move in a, let's say if we take an example, it's already turned left because it doesn't have that much roll stability. It doesn't counteract the gust, and it will fire in a spiral manner. Yeah, so the same as we seen on our roll stability, there is a horizontal tail blanketing. The same effect will be a vertical tail blanketing. And the last part is the crosswind landing. Yeah, so this is the interesting part that many aircrafts have to perform in a adverse condition. So if there is a crosswing from this way, so we are not trying to oppose the wind, because if we're trying to oppose the wing, we have to provide so much restoring moment to the aircraft. So pilot have to do larger work. So what they intelligent do is, they are while they are landing, they are aligning their aircraft in a crosswing, and at a time of landing, they are using all the power from the rudder to align with your runway. Yeah. So yeah, we can see from the mathematics that if the CM beta is too high, so data might require exceed the limitation part. So this is not like the design part will go in their own way, and then the stability part will come, and then they are going for a reiteration. As the designer engineer, we should know the stability part and design accordingly. So from this, we can just only say that the static stability is It's just a initiation for the equilibrium. It's not talk about in how much time it will be in an equilibrium. And everyone has some logo and all, so we are trying to one video by using AI. So we are just want to introduce our team in a formal way. It's just a funny video, so you can't see. Okay, one. Yeah.
Yes, your idea is really great. Yeah, and please, I think. I must definitely praise the Lord. Prof initially thought and gave us the direction that majority should be presentations only. Now I am enjoying it really. I think he's to be applauded for his suggestion of presenting. Really great. This question applies to both the teams that I presented. I just want you to draw the graph of CM alpha versus alpha. If you understand what I asked.
Yeah.
CM alpha versus alpha. That is dCm d alpha versus alpha itself in subsonic speed. The other team can also participate if you want to.
Yeah.
Any comments? This is subsonic speed.
Yes. Subsonic.
Symmetric airfoil.
Yes. Any airfoil. Cambered or any.
Any remarks from your side? The other team?
First.
This carries marks, sir. You don't answer.
This is for a stable area.
dCm by d alpha is not negating here.
dCm by alpha with respect to alpha.
People just keep quiet and sit. No, sit quiet. Review if you want to. He's claiming something there. No,
It is below the x-axis.
Yeah, so CM versus alpha. This is the slope. It's a negative.
Does it go infinitely?
Yeah. Some question here. Why don't you be bored? Achha, you want
Yes,
them to
that's why it's a constant.
Come on here, please. Ask if you want to.
Wait.
Any questions will be rewarded.
I have a question.
So can you please draw the
Up to a point when you hit point.
Yes. Then the graph will. After that point, the graph will. Yeah. Yes.
Hello.
Question
Okay. So I have one question. So can you please draw the CM versus alpha graph for positive cambered airfoil?
You take camber, you can take a paper also.
So my question is that can you please draw the CM versus? Okay, no sir, I'm questioning.
CM alpha versus alpha itself.
Okay. Sir, for the whole aircraft or for the wing?
You can take both ways. Draw for airfoil if you wish to. Draw for aircraft if you wish to.
So for the airfoil it will be I think constant and it will be negative, and for the aircraft this will be right. Yeah, for the stable. Yeah.
You are saying that CM alpha versus alpha is the top one.
Yeah. For the stable case, sir. For the stable case, yeah.
No, that's not. No.
That is negative here.
That's the CM versus alpha graph.
Yeah.
And we have to put CM alpha versus alpha.
He's saying the top one is CM alpha.
No.
This is CM alpha. CM versus alpha. This is CM alpha versus alpha.
His handwriting is very bad, sir.
Yeah, but they already drawn in their PPT. They should know.
Yes. Second cleanly drawn.
Okay.
For the complete range.
Okay.
Anyone who's addicted can go. Just one question. That's enough. CM alpha.
No, CM alpha. Yeah. One second. Yeah.
No, please, hold on. You approve this?
Approve it, sir.
Sir. I don't know the names. If other teams approve this graph, then it is your choice. Other teams will get or not get the marks.
Yeah.
Depending on body. Consider flat slate.
He's drawn as BCM alpha versus alpha.
Yeah. So after a stall, your CL itself it's a non-linear. So your CM will also.
In the normal regime.
Yes. In a normal region, sir, it's a constant.
Okay.
Yeah, it's a constant, sir.
We find behind the in the negative regime.
Yes, sir.
So it will continue like that.
Yeah. It will like same.
ऊपर जाएगा नीचे
Yeah. Yes. There are some. This is the region.
Okay. नहीं, my question is complete margin. वो उधर ऊपर जाएगा इधर नीचे आएगा या उधर नीचे जाएगा इधर ऊपर जाएगा.
Complete margin before a stall or after a stall?
I'm not talking stall.
No, sir. It will be the constant.
Any questions from the other team? Earlier team? You have to. Do you approve this? I know. I wanted him to draw the full. Any comments from others? If sir permits, draw an upward inclined slope from the graph. Left. Okay? No, left. Udhar se.
You can.
Okay.
Go to the point. You have drawn a straight line, no?
Yeah.
Yeah. Go to the left extreme.
Okay.
हाँ, इधर से ऊपर extreme. इधर से नीचे straight line. Okay. Yeah, that's just. Am I right? I think. If I'm right, how many are you with me if I say this is right?
Sir, the second entry is not.
So second entry will be a upper.
I think time बहुत ज़्यादा है. It's a tax. From inside it's over.
I'm told that some of you have classes at 4 o'clock. How many of you? Yeah. So sorry, but we wanted to give a level playing field for everybody because the first two teams have been given a lot of time. So is there any team who thinks they can finish by 4? Yeah, you can go next. And the remaining teams we will take up on Wednesday. Okay? So we will stick to the time and hereafter. So hereafter we will, but for this question, I just want the other teams not to feel that we gave only the first two teams a lot of time. So we will not restrict the other 4 teams also for this particular question, but for the remaining questions, we'll be very strict about
And 5 I think you should. I'm writing these graphs.
In fact, one of the slides, one of the persons mentioned that CM alpha is not a constant. It's like
Most of the time they know CM alpha is very easy to draw, easy to find in book. But if you say CM alpha versus alpha itself.
Good afternoon, everyone. We are Team Right Wing. I'm Tarishi, and we are giving our presentation on effect of stability margin on stability and aircraft performance. And let's call it a day because our entire presentation has already been given by other teams. I'm just kidding. So what is stability margin? Stability margin is the distance between the CG and the neutral point, and it in this formula it's normalized by the mean chord length. And neutral point, as was earlier explained, is used because it doesn't change its position due to the change in angle of attack. The moment remains constant. So in order to arrive at the condition of stability, we take a moment balance about the CG, and by non-dimensionalizing it by dividing it by dynamic pressure, we get the condition of dCm by d alpha is equals to minus Sm into Cl alpha, where Cl alpha is the slope of the lift curve. And we know that for a positively cambered airfoil, Cl alpha is positive, and to get a negative restoring moment for a let's just consider a condition of pitch up in an aircraft. So if we want to stabilize the aircraft, we need a negative restoring moment. So that's why we need dCm by d alpha to be negative. So according to this equation, stability margin needs to be positive. So we arrive at the condition that CG should be ahead of neutral point, and this will be further explained by Navya.
Good afternoon, everyone. Myself, Navya. Now I will explain you, before explaining my concept, let me explain you what is the trim of an aircraft. See, whenever the aircraft is in stable equilibrium state, that is steady unaccelerated flight, the pitching moment about the center of gravity should be equal to 0. If it is not 0, it will be subjected to rotational acceleration because of the unbalanced momentum. So we need to bring it back to the equilibrium state. That is our goal. I'll explain you the derivation part, how we came into the static margin and the neutral point derivation and all. Now the first equation will explain you the pitching moment equation, where Cm is equal to Cm naught plus dou Cm by dou alpha into alpha, where Cm is the pitching moment coefficient, Cm naught is the pitching moment coefficient at zero angle of attack, which will explain you about the balance of the aircraft. Next, dou Cm by dou alpha is called as the pitch stiffness. Alpha is the angle of attack. Now I'll explain you the graph. This graph, if you can see here clearly, this is the point where the aircraft is in equilibrium state. If the aircraft is getting unbalanced by any other external forces, effects and all, the angle of attack will be increased. So it reaches to a point B. So to bring it back to the equilibrium state, the aircraft must apply a nose down moment. So what will be the quantity of that moment? It is nothing but the distance of BC. So the aircraft has to apply the BC moment to bring it back to the equilibrium state. That is A. This is the positive stiffness and balance. This is the balanced but negative stiffness. So if the aircraft is in this lane and it has to apply the nose up moment to come back to the A point. This is for a fixed elevated deflectness and a given CG point. And now this is the other case where the CG point is not fixed. Like while designing, we are not fixing within the limit. So this is the other case where we will be having the unbalanced case. Now, as I told that Cm naught is used to determine the balance. So if you can see that, if the Cm naught, like I'll explain you why the reason Cm naught has to be always positive. Like the other teams, I don't know whether they explained or not. Why we are considering Cm naught positive, why not 0 or why not negative, can be explained from here. When at the end of the derivation, you will understand why we are considering. So Cm naught negative corresponds to the positive camber, and positive corresponds to the negative camber, which we also call it as a reflex airfoil. Yeah. This is other graph which will be explaining between the Cm and the Cl. So while deriving the position of the neutral point or the static margin, we require all these components and all. So this is the derivation part. You can understand it explains about the wing, and this is the part of tail. Here I mentioned only the important equations. The source I mentioned, if anyone are interested, can go through the entire derivation. Like it takes more time to explain all the derivations, so I mentioned the important points here. So I am taking the momentum about the center of gravity, pitching moment about the center of gravity, non-dimensionalized it, and compare it with the basic equation which was shown below. After doing all these things, we will be ending up with the distance of the neutral point from the leading edge. So this is the equation we will be ending up with, and this is from here we will be deriving the static margin. So basically the static margin will give you the range to have the, designing of a CG point. So static margin was defined as XNP minus XC, CG. If you can see here, from this graph also we'll be having the negative slope. This negative and this negative will be positive. So for a longitudinally static stable aircraft, the static margin should be always positive. So which will be corresponding to the less maneuverability. If it is negative, it corresponds to the more maneuverability. And my fellow teammate will explain how we can shift it.
Good afternoon, everyone. I am Karthik. Now that we've seen how we have achieved static margin, let's look at the ways how to increase the static margin. Just from the equation SM equal to XNP minus XCG by C bar, we know that if we want to increase the static margin, as in make it more positive, we either need to shift the neutral point more aft or move the CG more fore, as in towards the front. Moving the neutral point aft is achieved by increasing VH, that is the volume ratio, which involves either increasing the area of the tail or increasing the momentum of the tail, or increasing the tail lift effectiveness. That is the ratio of that is the d alpha t by d alpha w term. Moving CG4 is achieved by increasing the fuel loading more forward and placing the payload or moving the cargo with respect to transport aircrafts more ahead. Now, for a given aircraft with its design conditions fixed with CM0 and with its weight and its conditions fixed, how can we achieve a higher CL for a given static margin? With a given aircraft, its equilibrium condition, equilibrium point or its trim condition is corresponding to the point A, where the graph intersects the x-axis. Now, to achieve a higher CL, that means we need to shift that point more forward, to the higher CL value. Now, this is achieved with by two methods. One is to shift the location of the CG rearward, which changes the slope of the CMCL graph, but maintains the CM0 same. This is, although not very practical, as given with an example from the book from Francis J. Hale. It says, let's take an aircraft which wants to go from Mach 0.8 to Mach 7.5. It demands a CL increase of 0.473 to 0.538, corresponding to an increasing slope of minus 0.122 to minus 1.06, minus 0.0106. This entails a CG shift of 0.014 MAC, C bar, which is 1.4% of the chord. This might seem like a very small value, but typical ranges of static margin are 5 to 15%, and comparing it with the 1.4% shift in CG, that accounts to around 30 to 40% of the static margin itself, which is which is actually very large. For a very small CL slope change, the CG shift is actually very ending up very large, which is not favorable for our case. The better solution would be to add an elevator which generates a pitching moment that shifts the equilibrium position without affecting the slope by just which in turn does not affect the static stability too. Yeah.
Hello everyone, I am Anjali Singh. So let's just discuss how this static margin affect the performance parameters of the aircraft. First is, we are considering like different cases of the static margin, at high static margin how our aircraft will going to behave, and at low static margin how it going to behave. The first at high static margin, when our CG is ahead of the aircraft, like at the leading edge, the aircraft is like this. To maintain the aircraft at equilibrium position, the tail will generate a negative lift. So we all know with the lift there must be an induced drag also. So for the high static margin, we have that negatively generated with the induced drag. But in the case of low static margin, although the leading edge has a less point downwards compared to the high static margin, so in this case we required less negative lift to balance our aircraft. So in this case, the induced drag is also comparatively less compared to the high static margin. Okay, if we talked about the range or endurance, Range is basically the maximum distance our aircraft cover in a one go from that launching to the landing point. So as you know, as I told you that at high static margin, we need a negative lift generated, which results in a more drag. So because our fuel is to maintain the same speed, now our aircraft will require more fuel. So due to this, the aircraft will cover less range in the high static margin area. But in the low static margin case, as the fuel required by the aircraft is comparatively less, so more range can be covered in this case. Similarly, it's correspond with the endurance also. Endurance is how much time our aircraft in the air. As it has more fuel to travel, so it will in the air with a long time. So at high static margin, the aircraft has a more endurance comparatively with a low static margin. So now Anjali, we will continue.
I'm Anjali Vivi. So let's look into effect of stability margin on takeoff and landing. So during takeoff, one of the crucial phases is known as a rotational phase, where stability margin has a huge effect on. So rotation phase is when the pilot pulls up the control to make the nose pitch up so that it can get off the runway. So here, a high stability margin implies strong stability, and which requires more elevator control, and it causes high rotational speed to be taken, as well as more slower and more time to actually take off. So a low stability margin means there will be an easy rotation, but it increases the pitch sensitivity. So there may be a risk of stall happening. And as the SM goes lower, it reaches near zero, there will be a negligible restoring moment. So stall risk or even over rotation will occur. So let's look into the case of Air Midwest Flight 5481. Here, it was a domestic airlines starting from South Carolina and couldn't even take off the runway because the CG was more aft to so that there was a less stability margin, and because of this there was a loss of pitch control, and it crashed even before takeoff. Now moving on to landing. In landing, one of the crucial phases is flare, where stability margin affects. During flare, similar to rotational phase, the low stability margin causes easy rotation, which increases the pitch sensitivity and causes over rotation risk. So here we take the evidence of the Gulfstream G650 flight test crash, where it was made to land at higher angle of attack, which lead to deep stall, and due to this, the T-tail, there was the wing wake affected the T-tail, and which rendered the elevator ineffective. So it couldn't pitch down and land properly, and hence crashed. So from these examples, we see that flare should be smooth and predictable, and so does rotation phase. So for this, the 5 to 15% static margin is very much required.
Good afternoon, everyone. I am Vaishnavi. I am going to talk about the effect of static margin on maneuverability and control. So when we have positive static margin, it's already explained that positive static margin means more stability. So if the aircraft is more stable, there will be more restoring moment. So whenever there is a pitch increase or decrease, or there is a disturbance, so there will be a high restoring moment, which will again bring back the aircraft to stable and trimmed condition. So if the aircraft is highly stable, if we want the aircraft to pitch up or pitch down or to roll, we need more elevator deflection, which is primarily to increase the pitch or to reduce the pitch. So as we can see from the formulas, static margin and Cm alpha have a relationship, and even the elevator deflection is related with Cm alpha. So we can say that if there is high static margin, we need high elevator deflection to achieve the same amount of pitch up or down if it's highly stable. So we can say that it's less maneuverable, and the pitch response is also very slow. As we can see from this video, this is Boeing 777, which is highly stable aircraft. So this is very less maneuverable. So even pitch up or pitch down, the response will be very slow. And even we need very heavier control forces and larger control inputs needed for this maneuver. So slower turns and pull-ups and larger elevator deflections required. On the other hand, if we consider zero or negative static margin, the aircraft is highly maneuverable because small amount of elevator deflection can also lead to high pitch up or pitch down movements. So it's highly maneuverable. And as we can see that SU-57, here it's performing the Cobra maneuver. Only a small amount of elevator deflection can also lead to high pitch up movements. So in this case, having negative stability margin can lead to high maneuverability. But this requires fly-by-wire control. This cannot be controlled manually. So there will be rapid pitch acceleration and pilot cannot safely fly without augmentation. Coming to limitations, static margin deals with static stability. It does not determine dynamic stability completely. It will just tell about how much it affects the dynamic stability. It only addresses pitch. It doesn't tell much about the lateral and directional instabilities, and no information on oscillation damping or response time. Yet we know that short period oscillations, in that case, static margin will lead to higher dampening. When we consider static margin, it ignores control effectiveness and saturation limits. It cannot quantify trim drag. It will say that the trim drag will be there, but it will not say how much it will be. And it's valid for only small disturbance, linear flight. And it fails to account for aeroelasticity. It considers the aircraft as a rigid body. That's it. Thank you.
Any quick questions?
For directional stability also we can have static margin, right?
But it does not tell how much it can affect. But majorly it will affect only longitudinal stability in terms of pitch, because it mainly deals with the distance between the CG and NP. So during longitudinal pitch up or pitch down,
This also we can define. Like rolling it might be, but direct pitching and going both we can have some neutral point. Might not be same way. But define two neutral points for pitch and yaw.
But it doesn't quantify. It determines, but it doesn't quantify. That is, we mean to say. It doesn't quantify.
Nañjappā. Thanks. No, she's actually, she stole my cricket.
Okay, thank you. So in the next class, we will have the remaining 3 teams presenting for the same topic. Once again, you will have a free time just to be having a level playing field with the teams which presented today. So take as much time as you want, that's fine. But from Monday onwards, Wednesday's topic will be postponed to Monday. We will stick to the exact timings for each one of the questions for each of the teams. Okay, please cooperate. I think the primary reason many of the teams are going beyond is you're not looking at the other topics for the other teams. So if you do look at that, then you will leave out a lot of things. See, the question is what to leave out more than what to include. It's true that many of these topics are correlated, so you will not be able to avoid an overlap, but you can minimize it. Just take a look at the other topics in terms of what they involve and try to avoid that. So you're not overstepping into some other teams, whatever they might describe. Okay. So this is just for the remaining questions. As far as this question is concerned, feel free to present what you already have put up together. Yeah. Thank you.
Good afternoon to you all. Last time, while the presentations were done, one question remained unanswered. That is the CM alpha curve that I had asked. Guidance professor, he enlightened me at 12:30 in the night. So I'd like to mention it. I had gone to sleep. He had not yet. Till he answered it. I thought he will not respond to me. So I went to sleep, and he had. When I got in the morning, I came to know that he responded and went to sleep before I. Half I was wrong. He was teaching me. So it carried on. If you recollect, we take a simple flat plate. Okay, we keep the limit between 15 to 15. Okay. That is the linear limit beyond which non-linearity starts setting in, and there is no point in going to 40-degree angle of attack unless and until you are in the low aspect ratio, low Reynolds number wings, which are low aspect ratio wings of 1.5, 2 or even 1.5 span by chord ratio. Unless and until that is done, and low Reynolds number to the extent of insects where they are at around 1000, 2000 and all that. So we are talking about 10⁶ Reynolds number. Unless and until we touch that, this is our limit. We take a flat plate, we rotate it at least 15 degree and then slightly go up to 30 degree. In this case, you will find a profile like this. In this case, probably like this, and then in this case, extremely like this, right? So from which you can write a CR alpha. If it is a flat plate, it goes through center and then it drops off like this, and then the reverse happens. Okay. If you take the CM moment coefficient, if it is not cambered, it is this is the CM versus alpha. Now what I had asked was CM alpha versus alpha. That means slope of this and slope of this and slope of this. Suppose it is cambered, then it is some negative like this, right? So now if we draw that CM alpha versus alpha, it would be, because CM is constant at aerodynamic center, if you remember. So CM alpha is 0. So it would be absolutely this. I take a different color. And any guesses what will happen here? What will happen here? Up? No. This is what happens. And this is also not perfectly correct, because the non-linearity here starts decreasing the slope and thereafter it goes to stall. So we won't know exactly the complete mechanism in it. Next point is, as you increase the angle of attack, the leading edge starts to shed vertices. They are called leading edge vertices. And in the low Reynolds number, they are the point of lift consideration. In insects and birds, at low Reynolds number, leading edge vertex is the one which produces lift, for your information. They produce 4 times the lift of an aircraft at low Reynolds number at 40-degree angle of attack. You can't imagine. So leading edge vertex is a very dominant phenomenon, and in our case aeroplane, leading edge vertex will separate the flow and then destroy the lift. That's what we understand as by stall. Therefore, it is non-linear, and that curve is not understood since the vertices will start off. And then it leads to absolute separation at the top, and further study is, I think there is one book that I remember, Joseph Rahn, that is high angle of attack aerodynamics. I don't know, sir may enlighten us with some other information on it. That book and all gives you with when you go in higher angle of attack. Otherwise, somewhere close to this and somewhere probably non-linear, linear, maybe the answer that we were looking into. That answers the question. Then it comes to a little bit of military danda that I wanted to give. I have taken permission of Prof. One is that, gentlemen, you are here in Mecca, Medina of India. Please don't forget that. You have been given a golden opportunity and you want to miss it. That is your choice entirely. But discipline and decorum of the class has to be maintained. You understand what is discipline. I am a military man. You understand what is decorum. Timeliness and silence in the class, participation in the class, all these are absolutely necessary. It is not that you are presenting to yourself for your evaluation. No. The topic of flight and space mechanics starts from flight mechanics, statics and dynamics, flight dynamics, then space mechanics, space starting off to the docking to the dynamics and orbital mechanics. It is such a huge topic that no one can really cover the whole thing in one small given space of time. And sir is doing an absolute in my perception, he is doing a wonderful idea that is being tried, and all of you are presenting everything together, and then everyone is getting enlightened out of it. He will take the classes later, but initially you are all coming into the jargon. I don't know how many of the professors will give an opportunity like this, but this is a wonderful opportunity. Don't miss it and mess it. Presentation for learning, please keep silence, ask questions and learn. You may or may not get another opportunity in your life. Passing out of IISc and going to an organization and then getting thrown out because you didn't know is a definitely disregard. I told you already, discipline and decorum, silence and audience. Audience, I mean you should participate and I should tell. Or somebody speaking here, you should listen, and then somebody listening here should ask. It is mutual, it is not individual. And then presentation is not for evaluation, but complete coverage of the topic that he has given an opportunity for. Please utilize it, don't let it go. This is the last class wherein we will have 2 presentation or 3 presentation left over, wherein time permission will be given. But otherwise, we are going to maintain 10 plus 5. Whether you present or not present, 10 minutes you will be walking out. 5 minutes is for questions. That means if you are 5-member team, 2 minutes each, 2 slides each, make yourself comfortable and present it and walk down. That's it. Please, gentlemen, when you are looking at the topics, which are 13, please read the topic and please read the question that is asked. Last time I found somebody deriving complete, static stability starting from directional stability, longitudinal stability to directional stability and to the roll stability. We didn't ask for it. If you look at static stability itself and the performance, you can think of that itself into so many individual each topics, subtopics. There is a need for you to coordinate with your own groups. What the other one is presenting is also important to you. And henceforth, that is where I would like to, what Prof has told, I would like to emphasize upon. If there is a repetition between the groups, the group will be kept null and void. You have to present something else. And the topics are given such that there is a meaning and there is difference. So scope is important, presentation time is important, subject, maximum individual 2 slides, I also told you. If you don't, now next is somebody went on, last time they went on to saying, this is derivation I have taken from somewhere and then I have just plotted it, I don't know. I heard one person saying it, I don't want to come out who said it, but it has been said. If you don't understand a derivation, please do express it. There is our guru sitting here, he will tell you how to go about it. That is the reason he is taking the class. Please come and tell openly, it's okay. I accept, I don't know. That is the boldest decision that you can undergo through first before you uplift yourself. And he will tell you what to refer or what to do, or he will derive it and show it to you. If you understand, please show it and then explain it. But if you don't understand and then show it, that is absurd. Don't show equations and derivation just for the sake of it. Last thing I already told you, coordination between the teams, no repetition. Repetition will be rejected unless absolutely found necessary. And last time sir also has mentioned that there has been right away cut copy paste from book. It is absolutely unacceptable. It has to be in your own words. In fact, one lady presented a handwritten derivation and a scanned copy. Really, I appreciate the effort. That is what is wanted. You understand in your own way and then you put it here. We would like to see that and you have understood it. In fact, sir used to say many shlokas when for the learning process. I don't have so much of time. I would like to get back and the presentation to start. But it is the mutual understanding and the inculcation of what has been told to you into your brain so deep that it becomes your own conscious present. You have to know it like your bread and butter. Blood and butter. I wouldn't even mind to say that. So please take care. All the best.
The first team can go.
Okay, so we'll be presenting on dynamic instability of aircraft and its effect on performance. Our team is Puṣpak Pioneers. And just to summarize, so we have drawn here so that in case when we refer to directional stability, so that is like if you get a yaw, how you respond, you want to reduce the beta. Similarly for lateral, which is roll. So if you get a roll, roll disturbance, so how you respond to that? That is lateral, and longitudinal is this, in the pitching plane, just to refer for the later slides. So we'll be covering about the definitions, then longitudinal stability modes, lateral stability modes, which are usually seen. Then we have done some simulation where we tried to simulate the aircraft modes. And then 2 case studies we are presenting where this became fatalities if we're not taken care. So my teammate Harika will start.
So good afternoon, sir. I'm Harika. So I'll just give a brief about dynamic stability. So stability, like there are 2 types of stabilities, like static stability and dynamic stability. So static stability is an instant response to the disturbance, and dynamic stability is a disturbance, like response to the disturbance over a time, of a period of time. Like there are 3 types of dynamic stabilities: positive dynamic stability, neutral, and negative. So positive dynamic stability is when a disturbance occurred and the if the oscillations keeps on decreasing and comes back to the original position, then it is called positive dynamic stability. And in neutral stability, the oscillation continues throughout the over period of time. And in negative, it keeps on increasing, the amplitude keeps on increasing, and it is analogous to the system of spring mass damper system. So same as in dynamic stabilities, it also has a second order system, and it can be classified in overdamped, critical damped, and underdamped based on the damping ratio. So that's how we can also differentiate the stability, dynamic stability, based on we get after solving all of this, we get equations in form of x dot is equal to ax. So if the matrix A has a real part of the matrix, eigenvalues of real part of matrix A was negative, then it would be positive dynamic stability. And if it is 0, then it will be marginal stability, which is neutral. And if it is greater than 0, then it would be unstable. So for equations of motions, like we first get the force equations and momentum equations from translation equation of motions and rotational equations of motions. And the Euler equations we get from deriving the angular velocities from inertial frame to body frame. So after linearizing all the equations, we get equations in these equations, and after expressing the perturbations to Taylor series, we get those equations, which is in the form of x dot is equal to ax, and later we my teammate will.
Thank you, Harika. Good afternoon. Myself, Bhavika, and I'll be explaining on the longitudinal modes, which are short period oscillation and Phugoid motion. So, whenever an aircraft undergoes longitudinal perturbation, it responds in underdamped oscillations, which are short period oscillation and Phugoid motion. On a very surface level, as explained by Harika, the equation of motion is 6 degree of freedom equation, which is linearized, and we make certain assumptions. The assumptions are the flight is symmetric, that there is no side slip and no roll or yaw. So we get the longitudinal motion governed by only 4 parameters, that is u, which is the x direction velocity, w, which is the z direction velocity, theta, which is the pitch angle, and q, which is the pitch rate. So this dynamics can be represented in state variable form, which is x dot equal to ax, where we get the A matrix. The A matrix is shown here, which we get from linearized form of equation of motion. We have taken a typical example of Boeing 747, which is under a certain flight condition, and we get a A matrix as such represented here. Since A matrix is a 4 cross 4, it will yield a characteristic equation of 4 degrees. And since it is an underdamped oscillation, so it will have eigenvalues or roots in complex conjugate pairs. So when we analyze these roots, we see that the short period motion, the short period oscillation, the real part of it represents how damped motion is. So when we compare the Phugoid motion and short period motion, we see that short period motion is heavily damped as when compared to the phugoid motion. Coming on to the complex part of the route, we see that the complex part represents the frequency of damping. So on comparison, we also find that the short period motion is have a high frequency. In short, that means the time period for short period motion will be quite short. The time period also is shown, and we can on comparison say that the short period the short period motion's time period is 9.13 and phugoid motion is 46.9, which is almost 5 times the short period. On to the next. In conclusion, we can say that the short period motion is associated with heavily damped, high frequency, short period of motion, and is and changes with angle of attack, whereas the phugoid motion it attributes to low frequency, lightly damped, and a longer period of motion, and which involves changes with theta and u. The table here concludes the entire the differences and features of short period oscillation and phugoid motion, and the figure here explains and illustrates the oscillation of both the modes. I'll give it to Surbi. Thank you.
Similar to longitudinal, now lateral. So as in lateral mode, there are two predominant motions, which is rolling and yawing. So depending on the characteristics which the in which the aircraft is designed. So either the aircraft could have both. So there are two modes of stability, lateral and directional. So if the both modes are responsive enough, that is one case. We'll see eigenvalues, but eigenvalues just tell you the response. So overall, the thing is, if both the response in yaw and roll are almost similar, we'll get one mode. If the one response is pretty high, one is say roll response is pretty high, we'll get roll damp mode. If the response in directional mode is very high, yaw, so we'll get the spiral mode. But if both are almost similar, then we'll get the Dutch roll. So all these phenomena are just because are a combination of what kind of aircraft you have designed. So if it is damping in one but not damping enough in another, you will see one mode. If it is damping in another, not damping in one mode, you will see the another phenomena. So we are just trying to explain that. So I am covering. So there are three modes in lateral plane. So there is roll and then there is yaw. So if the roll damping, so if the eigenvalues, obviously we can't go to right side, that is an unstable mode. So this is the plane we have, and now there can be many combinations, right, of eigenvalues which we'll get. So if we have a eigenvalue which is very far left of it in roll, so what we'll get is a very highly damped roll oscillation. So whatever disturbance comes, it will damp very fast. So it is sort of a short period in longitudinal. It is analogous to short period in longitudinal. And then, so that is the roll damping mode. And what are the issues with that? So there are two. Now this can be either this side or that side. So if the time period is very slow, the response is very slow, then it is sluggish. Then even if we are trying to roll or giving a maneuver or trying to bank, then also because it is slowly responding, we won't know that actually it has banked. So we'll give it more than what is required and we'll overshoot and then we'll try to correct. So that sort of thing will happen if it is very sluggish in roll. So obviously one solution is if you reduce the inertia in roll, you can get a little higher response if you're facing with this issue. Now another thing is if it is very fast, that it is responding very fastly in the roll, then what will have, obviously if it is very fast, you'll get a jerky and noisy motion. You'll try to bank and it will sort of do a very highly oscillatory motion. So then we'll need to have a reduced sensitivity. Otherwise, a small in a joystick, a little bit here and there, if you press also, it will make it very jerky. So there you will try to reduce sensitivity. So this is the issue which will have, even if the roll mode is either too slow or too fast. And this is the sort of thing one would expect to do to mitigate it. So roll disturbance, I anyway told that it is a damping in roll, and it is so this is the lateral directional disturbance. Then there is spiral mode. So here there are two cases, right? So one is either roll is too responsive or either yaw is too responsive. So spiral mode is when yaw is very responsive and roll is like trying to catch up. So what happens in spiral mode is by any chance you get a disturbance in bank angle, you will roll. As you can see here, so as you bank, you will your lift vector will say you are banking. You got a bank angle in the right side. So lift vector overall will get towards right. Now since the yaw is and because of that you will get a velocity build up towards right. If you got a bank, your lift vector will create a velocity delta v. So you will try to turn right. So you will get a beta. First of all, because of delta v, you will get a beta. And because now directional stability is very high, so it responds very fast. So as soon as beta occurs, you it rotates with a very high angular rate. So the R which is built up, which is the angular rate, that becomes very high. Now what happens is, because there are two wings, right? So if you see the incidence velocity, because of the R omega component, here you will see locally the velocity is higher and the inward wing the velocity is lower. So because of that delta difference, you will get a higher lift and drag in the outer wing if the bank was like this, and you will get a lower incidence velocity in the lower wing. So higher lift, so it will cause a roll. So further, this whole thing was caused because there was a roll disturbance in this direction, right side, and then because of the high yaw response, you are even further increasing the roll. So it sort of goes into a spiral. So roll creates yaw, and yaw is very responsive. Yaw creates again more roll, and then you sort of dive, and because the lift vector is constantly turning, right? Lift is constantly rotating in this direction. The vertical component is not enough, and you are rotating as well as sort of sinking it. So that's what is the spiral mode. So this is all because of very high strong directional stability and a weak lateral stability, diametral stability. So this is what I've shown, graveyard spiral, because eventually it will crash. So what are the issues? First was this, because of spiral mode, if that mode occurs, and you have to design your aircraft accordingly, that you should reduce the tail size if you are seeing that this sort of thing can happen. So one is graveyard spiral. Then if the unstable time period is very hard, fast, then you will not be able to trim. Even if for banking, you will not be able to trim. Then if it is too stable, then too stable as in key, if you are trying, if you overdo, if you reduce the tail too much also, then if you get a gust, you will not be able to do the directional stability enough. So there is a good size of tail which has to be designed. Not too high, otherwise you will see this. If it is too low, then you will see the next issue which Apur will be telling. So, and then if it is too stable, hard to land in crosswinds. That is, of course, if you don't have if you have a very big tail. So what is the mitigation? First of all, this is caused because there is a good directional stability but not enough in roll. So obviously you would want to increase the dihedral and reduce directional stability, which is size of tail, and then hold. If you are seeing, you have to hold the heading. You should not let it rotate. So that is one thing which a pilot can do. So this is for spiral mode. And then the other case, which is the other extreme, where roll stability is pretty high and directional is less, that would be covered by Apur.
So, as opposed to the spiral mode, the Dutch roll occurs due to a weak directional stability but a stronger lateral stability. Now, many factors can contribute to this, maybe a larger dihedral angle and a shorter vertical stabilizer. But what's the mechanism of Dutch roll we can see here? So the Dutch roll initiates due to any disturbance that first initially sets up the yaw oscillations. So if we see, initially there's a deflection in the side slip angle, and once the side slip angle has reached its maximum value, and because the lateral stability is quite high, it will take some time to generate a free roll response compared to the yaw response that we see here. So at the maximum yaw deflection angle, now the vertical fin is generating enough counter moment to again bring back the aircraft to the flight path. So what happens is once this moment builds up, it starts rotating the aircraft towards the opposite direction. Meanwhile, the roll response starts lifting the wing that is exposed directly to the side slip velocity. And therefore what we see here in Dutch roll is quite counterintuitive. As in bank angle, what we see is while we are banking, when we are banking towards the starboard side, the right wing would dip and the port wing rises up. But in the yaw response that but in the roll response that we see here, while it is yawing towards the flight path, if it starts yawing towards the port side wing rises up. Hence, and it continuously keeps losing altitude because the lift vector is barely aligned with the direction of the weight of the aircraft. Thus, the Dutch roll that you see here and the yaw angle and the roll angle are lag by 90 degrees over here because if you see, the roll angle affects the tilting of the lift vector. That implies phi relates to L cos phi, and lift in turn affects the side slip acceleration. Meanwhile, beta, that is the side slip angle, affects the side slip velocity. Hence, to relate these two, theta affects acceleration, beta affects velocity. There's an integrator between these two. And in any oscillatory system, if there's a time integral, that implies a 90-degree phase lag between the two. So, and if we look at the eigenvalues of the plant matrix, we see that the frequency of the longitudinal short period mode is similar to the Dutch roll mode. Now, apart from this aerodynamic coupling of the roll and yaw, there could be another thing. If we look at the rotational equations of motions, we see that we have neglected the product of inertia terms here. That is I1, I2, I3. We are assuming that the principal axes are aligned with the coordinate axis of the body frame. But I was interested in finding out what product of inertia effects could play a role in this coupling. So there are barely any studies on modern aircrafts, but the publicly available data is from 1950s to 60s. That was done by Fairey Aviation and upon their experimental aircraft Fairey Delta II at a 40,000 feet altitude. So what we see here is that if the principal axis is tilted 1 degree upwards, that is nose up, that changes the product of inertia term increases the product of inertia term by 50 degrees, and the damping yaw derivative by 12 degrees. Damping yaw derivative is just the derivative of the opposing moment of the fin with respect to the side slip velocity. So higher the damping yaw ratio, better would be the stabilizing effect of the fin. So Fairey Aviation did some experiments but they did not plot anything specific with respect to product of inertia versus the stability curves. They were more interested in the Mach number effect. But then further studies were done by Naka group, and what we see here is that if the principal axis tilts up by 2 degrees, the stability region, that is as the yawing moment coefficient, the derivative of yawing moment coefficient with respect to side slip angle increases. This measure, the higher magnitude of this measure means the greater is the stabilizing effect of the fin. Hence, the regions above these curves represent the stable region, while below them represents an unstable region. Thus, if we see, if the product of inertia, if the tilting of the principal axis is 2 degrees, the curve becomes, the stable margin increases quite significantly. This is the plus 2 degree inclination. While if it tilts nose down, that is minus 2 degrees, what we see here is the stability margin decreases quite significantly. This is the zero product of inertia term that we have shown here. So why this product of inertia? The existence of product of inertia means that any torque that is applied or the moment generated by the vertical stabilizer instantaneously couples the roll and yaw motions. Unlike the aerodynamic effects that lags by 90 degrees, this 0 degree response interferes with that 90 degree response, and thus if this response is in our favor, that is it opposes the side slip that is being caused by external effects, it will act as a stabilizing effect on this aircraft. Hence, we can reduce the Dutch roll modes and they will naturally die out if they are in the stable region. Hence, we can reduce these Dutch roll oscillation frequencies if we carefully distribute the mass across the XZ plane, that is the longitudinal axis and the yaw axis in that plane. Further will be explained by Michael.
Good afternoon all, I'm Maiko. So I'll be talking about handling qualities, which relates to how the pilot would rate the aircraft performance and how it relates to the certification of the aircraft. So on the left we have a flow chart which describes basically how a pilot would rate the aircraft based on few basic questions. So we start with whether the aircraft is controllable, then is it controllable with adequate tolerable pilot workload, and then is it satisfactory without improvement or not. Based on these answers, the pilot would give a rating to the aircraft, and then further decisions would be taken whether the aircraft should be modified or not. So you can see the rating 1 is the best rating and the rating 10 is the worst rating. So based on then we can drive the direction of the aircraft design. And on the right we have a graph from the military standard 8785C. So, which is also related to flying qualities. So it separates the categories of flights in A, B, C and lays out 3 levels of acceptance criteria. So here is an example of category A flight phase, which is non-terminal and rapid maneuvering. An example of this could be air-to-air combat, very relevant to the combat aircrafts. So this example is related to short period frequency. So in the table we see the damping ratios, the minimum maximum range for various level of acceptance for the short period oscillations. So we see that level 1 damping is the highest and level 3 is the lowest. So in a way, in oscillations you want high damping so as to not have it oscillate too much, but also not too much because the response would then be sluggish. So we can see that there's an ideal range of 0.35 to 1.3 in level 1, but 2 still relaxes the maximum damping ratio. But we would ideally want it between 0.35 to 1.3 for the level 1 acceptance. And in the graph, we have the frequency of short period oscillation versus the load per angle of attack. And the graph shows the level 1, level 2, and level 3 ranges of acceptance. So after this, we have, in this presentation, we have seen the various modes and how the dynamics perform. So basically, we'll now, in the next slide, we'll see a visualization of all the modes, which has been recorded in a flight simulator video game. So yeah, so I had a few military aircraft replicas made in the video game. So now there's a disclaimer, since we have an Air Force person here. So I'm not saying I know how the aircraft flies, but it flies like that in the video game. So we'll go to the next slide. Okay, so the first will be the Dutch roll, which is the Su-57 here. So I'll give a yaw disturbance. Yeah. So I give a yaw disturbance right now. So let me play it again. I'll give a yaw disturbance, and you can see there's a Dutch roll sort of a thing, but it dams out quickly. So yeah, and the second is the short period oscillations, which is on the MiG-21, but I don't know how MiG-21 flies, but this is how it flies in the video game. And here you can also tune the gains and the damping, so as to get a performance you require. So you can see it has an oscillatory movement, which is the short period oscillations. Then the third we have roll. Now the roll is, you can see it's very sluggish here and it's very highly damped. So while it's rolling, I give me the command continuously, but as soon as I leave it, it stops immediately almost. So yeah, it is very damped and it damps really quickly because as you saw in the graph before, the roll eigenvalue is at the very far in the left. So it damps really quickly. The fourth one is the Phugoid. Now it will not look appreciably clear in that, but what I am trying to do is that I am trying to stabilize that aircraft around 1000 meters, which is not clearly visible here. So I am trying to fly it around 1000 meters, but since it's not perfect, so I need to keep correcting it for a longer time, and that's why it's a long period oscillation, and which is the Phugoid oscillation. So we only have 4 here, not the spiral one. I was trying to get the spiral one, but I couldn't get that instability at all. So I could only record 4 of them. So next up we have few case studies which will be taken up by Bhagishri.
Good afternoon, everyone. So till now we have seen equations, we have seen simulations. So let us take up some real life cases that has taught us a lot. So my case study involves Boeing KC-135R Stratotanker, which is a US Air Force refueling type aircraft, which crashed near Kyrgyzstan on May 3rd, 2013. So before I go to the technical discussion, I want to respectfully note that this accident involved, this plane had 3 crew members who, all these 3 souls perished in the accident. So let me start with the sequence of actions that caused this accident. So shortly after takeoff, the flight control malfunction occurred, and after a certain amount of time, the rudder started deflecting in an uncontrollable manner, which is because of the malfunction, and it entered the rudder hunt mode. So rudder hunt is basically the rudder is oscillating to and fro from its former position, which is also affecting yaw and roll because we know it's coupled, right? So that rudder hunt caused the undamped lateral directional mode, which is Dutch roll. So this aircraft entered the Dutch roll mode, and unaware of the situation, there was an attempt made to turn the aircraft using the rudder. So we know that rudder use during the Dutch roll is very phase sensitive. So it will either dampen whatever is happening or it will add energy to the oscillation. But unfortunately, what happened in this case is it added energy to the oscillation and it started, the oscillation rate increased per each cycle. And so the Dutch roll amplified until it reached a time where the acceleration forces faced by the aircraft exceeded the structural limit of the tail section of the aircraft. So the tail section broke off. So after that it crashed. So basically this is the sequence of actions that caused the crash. Now if we look at the technical side, basically what happened was the roll and yaw damper channel that malfunctioned. So basically the damping system was somehow responsible for this crash. So after this accident happened, there was an investigation board, of course, and then they made an upgrade to go to series yaw dampers. So earlier the older models were having the parallel series dampers, so that was somehow coupled with the rudder pedals of pilot. So this time what they did, the R feedback, the series yaw dampers, that would take yaw feedback directly from the aircraft, and then it will put the rudder command which is independent of the pilot, and it is, of course, it is in series. So it does not, like if we look at the detailed view, like if we look at the detailed incident, we can also see that the yaw damping had somehow affected the rudder pedal. So that was also a reason for which the pilot was unable to control it at that moment. So this is the upgradation we got after that accident, unfortunately. And here I have attached some references for some detailed view. So next will be another case study by Pragya. Thank you.
Good afternoon, everyone. I am Pragya. I'm going to discuss about a plane crash, a passenger plane, JAL 123. It happened in 1985. And what happened exactly here was there was an improper bulkhead repair. Before 7 years prior to this incident, there was a tail strike on the ground while landing. So this back section has to be repaired, and there was some error in the repairing, due to which during the crash there was a cabin pressure leakage, which created a hole at the tail side, and due to which the rudder also started to shed off. After the shedding of rudder, there was uncontrollable yaw motion, and yaw and roll are linked, so there was Dutch roll started. After that, there was, when they were trying to get the plane down, like plan to landing, diving, so there they had, when the plane was near the earth, near the surface of the ground, it gained velocity, due to which there was lift again. So it started Phugoid motion, Phugoid oscillation. And after those Phugoid oscillations, they were become uncontrolled, and there was loss of control by the pilots. And the pilot tried to keep the flight in 32 minutes after knowing that there is a problem in the tail side. And there, this is it, and it crashed near a mountain. So in this crash, there were 520 lives. 520 people were dead in that crash, and 4 survivors were there. That's it. Okay, so conclusion. We have discussed about the 3 modes of stability here: longitudinal and lateral and directional. And then there were simulations using the video game. Then handling qualities by Micro, and 2 case studies highlighting the hazards. Thank you.
Any questions from the audience?
Can you explain the parameters in the A matrix? What are all parameters? Maybe the XU, XW, ZW.
This slide only, right?
What are all those parameters?
Yeah, so XU, X is the force in the X direction of the aircraft in the body fixed frame, and X substitute U is a derivative with respect to U, and W is derivative with respect to W, and the Z is the lateral force with respect to, sorry, not lateral, vertical force, which is basically in the direction of lift. That is again subscript U is a derivative W with respect to U, and then W. Then U naught, W naught are the equilibrium speeds, the reference speeds, and G cos theta, G sin theta are the components, and theta naught is again the reference value of theta. Mu is the mu is the moment about the aircraft with respect to U. We have then a moment with respect to the rate of W dot, and again the Z with respect to U, which is the vertical force, and then again the moment with respect to W dot, and again ZW, and then Q is also the moment with respect to the pitch rate. Yeah, moment with respect to the pitch rate, and I2 is the moment of inertia about the pitch axis.
Can you go to can you go to the root locus diagram? I just want to know how you, like how with respect to those poles, how you able to get, okay, this is this mode, like spiral mode, roll, damping, and Dutch roll.
So if you see the real part, okay, only Dutch roll has the complex roots. So Dutch roll, because it is an oscillatory thing. And if you see the damping part, the roll root, which has the highest damping, that is the roll mode where you sort of get 2-3 and then it will die off. So any disturbance there is very much highly corrected. Then the spiral route is very almost sometimes it is in the negative side, sometimes it might come at the positive side. Actually, no one will design the positive side as such, or if they do, then they have to put a lot of control action. So spiral root, because that is also non-oscillatory. If you see, it is like growing in one direction. So that like intuitively also we can just feel.
No, my question is like, if you get some eigenvalues,
Yes,
you
yes.
solve the eigenvalue problem. Based on the values, how you identify this is the mode? Like, let's suppose you just mentioned here, right, the spiral mode, the roll damping, and the touch roll. Those values.
Sir, where they do they look lie in the left half plane, right? Like, so if the magnitude is very low, the negative part is very high, then it is like these. So these whatever names are written, spiral mode, roll damping, touch roll, these are just approximately phenomena which have been named, but it's not like if there is something in between here. Oh shit. Sorry. If it happens here, see, it's like which mode, which motion, your stability and roll stability, which dominates. So you might get a combination of these. It's not like one I get, like you'll get a system. You might see these, whatever we'll get based on the A matrix. So based on the aircraft design, we'll get different modes. And based on the magnitudes, we can just classify them. So if it is very left side, it is roll damping. If it has complex conjugate pairs, that means both are feeding in energy to each other. That's what Apoorv told, right? Like, so.
What is the significance of the imaginary number in the oscillator? What does that mean?
The frequency.
Other two values, it doesn't have a imaginary part.
Yeah. Because they're not non-oscillatory.
Okay, the imaginary part, what?
Oscillation.
What is it?
Frequency of oscillation and oscillation itself. If there's no imaginary part, there's no oscillation. Just simply exponentially die down. So, A matrix is just that dynamic CGPA equation of motion in state space.
Thanks.
Can it take a little time, sir? Okay. First, as I had initially, or professor had, in fact, nothing I, it is all prof. As professor had earlier mentioned, you have gone into derivation of Dutch roll, spiral divergence, Phugoid, and all that. Can you derive them?
No, we are not
Please, straight question. Can you derive them? Any one of you? Starting from here now. Yes or no?
No, sir.
Good. Second question. Do you know what is an eigenvalue? What is an eigenvalue?
If you have a matrix, if you sort of...
No, what is this physical significance of an eigenvalue with respect to these?
How much damping will...
No. Any one of you? Anyone in the class can compensate. The same marks will go to you. Does anyone know? First question I asked, what was it? Do you know what is Phugoid? Do you know what is Dutch roll? Do you know what is camel ride? Do you know what is wing rock? Do you know what is spiral divergence, tight spiral, liberal spiral, spring? Are you aware? Anyone in the class? There is already a question in the series which professor has mentioned, so that you can go into those physics and understand each one of them physics wise, not derivation wise at least. Why did you jump into this?
So, we'll
One
look at-
simple question.
Yeah.
Show me the Phugoid in this aircraft. Hold the aircraft and show me the Phugoid. Hold the aircraft. I don't want any others to help him. He is going to join, let us say, Air Force as a maintenance engineer. I don't want you to show. I want him to show.
No, I was talking about
Please
eigenvalues.
show me the Phugoid holding this aircraft. How does it behave if it gets into Phugoid? Hold the aircraft. The aircraft is in front of you. Hold it. Show me the Phugoid.
Like it will
You all agree?
oscillate about the longitude axis.
Is that Phugoid? I don't want reasons. Is that Phugoid? It's camel ride.
Yeah.
And now coming back to the question. So for the full class, what is eigenvalue?
So, sir, the eigenvalue is if we look at the x dot equals ax equation.
Okay, I'll give a clue. What is the relation between eigenvalue and stability?
Positive eigenvalue. Yeah.
Are you sure? Okay, I'll give another clue. What is the relation between eigenvalue, pole, and stability? Pole is in the control sense that you said here. I'm now clearly laying out all three branches: controls branch, stability branch, and the physics. What is the physical significance of eigenvalue here?
Positive eigenvalue would mean any response that is.
Is that so?
X. Yes, I mean.
No.
Just.
No. Eigenvalue is eigenvalue. There is nothing called positive negative.
Okay.
Right?
So
for a matrix, eigenvalue is eigenvalue.
It's a magnitude of that only we are talking.
Eigenvalue is unique. Right? For a given matrix, eigenvalue is unique. What do you mean by more eigenvalue, less eigenvalue?
No, the magnitude.
So if somebody gets into that eigenvalue, then there is a discussion. So what is eigenvalue?
it is the along which there is only stretching or squishing of the space.
No, suggestions. So that means these questions are unanswered, right? So you have still an opportunity for you to go back, study, and attend the next topic that has been given already. Phugoid, Dutch roll, everything is specified in the stability portion of this, which you will select here. So please be careful. Such questions should be answered by you having gone out of IISc. Now, what you didn't do, how does dynamic stability affect the performance? You all spoke about dynamic stability. The question is, how does stability affect the performance of aircraft?
See, we majorly covered.
What is performance?
Endurance, range covered, how much you can control, maneuverability, then
Fuel consumption, passenger comfort,
and we have only
landing,
about,
takeoff.
maneuverability and passenger.
So where are these performance parameters here?
Only maneuverability and passenger comfort is what they have.
So you really, this applies to the whole community of the class which has presented. That means all your presentations were like this only. I'm pointing it out intent. I mean, Prof has given me this brief before we came here. He has told me to speak about this. That's why I'm speaking. Otherwise, I would keep quiet. So you spoke something else when the question was itself available for a next opportunity. And that too, you didn't know what was it. If I am right, sir, correct me if I am wrong. Eigenvalue is a stability point. It is the point at which it's like neutral point. It is the pole. Adjustment of the pole will give you, depending on where do you place, what force you apply with. Am I right, sir?
Well, it's two different kinds of interpretations.
I mean, to some extent, I don't know. Yeah. So eigenvalue has that physical significance. So if you say spiral divergence, it is an eigenvalue to which if you enter, you will enter into type divergence. Am I right, sir? If I say so. And Phugoid is again eigenvalue. If you enter into that eigenvalue, you will enter into that. Now, can you really, with the nonlinear equations, how much of non-linearization has taken place? Is there a closed loop solution to this problem? So,
Computationally,
these are all my
theoretically for a very it will take time and
comments. These are all my comments. No questions to the class also. So next time when you are presenting, please focus, please concentrate, please distribute, communicate with each other. The physics is most important. You should, when you go out, when you say flight and space mechanics, proudly know these things well. It's only comments.
Sure. Yeah. Well taken. The Air Force officer speaks in the military language. But essentially, what is important over here is this whole exercise is a learning process, right? The way it has been devised, a lot of thought has been taken in terms of the 13 questions and also the subtopics that have been listed. Okay. If you stick and focus to that, then I think we will have a much more wonderful experience designing the presentation, actually talking about it, and then learning from the others as well. So that is the main point. Not to take away from especially your team, the presentation has been excellent. I really congratulate you in terms of the effort, thought, and a lot of interesting aspects that have been brought about from the accident investigations, from the video game interpretation. See, it's not just about the video game, but the way you interpreted it. I really liked it. All these are very, very important, and I really appreciate it. Okay. So don't take it in that sense. But remember that this is the last question for which you're allowed free time in terms of how much our time you want. And that is something that I already told you. And so there's absolutely no penalty for that, right? But from the next question onwards, and this holds for everybody in the class, I want you not only to look at that particular question's subtopics, but also the remaining questions, what they are about, and also what the subtopics there are, because at the end of today's class, as suggested by one of you, we would be having lots to pick up the subtopics. So ensure that you stay focused on this particular subtopic and also the particular topic, okay? Because there are certain things which are going to be covered later. For example, this question is about performance in general, but the next question is also about stability's impact on range and endurance, which are also performance parameters. So you do not want to bring in that aspect of range and endurance into this particular question. So that's exactly what I'm trying to convey over here. The whole idea of these presentations is I interact with a lot of the industry. A lot of our alumni are working with the industry. Many of them are doing great job. But in the initial stages, especially when they are interviewed and also during the training period, a lot of the industry members have had issues with our students in particular. And one of that was, even though many of you guys will know a lot of things, when it comes to the context, how you interpret that knowledge, utilize it and apply it, I think that's where a little bit of time it takes in the training. And they would want the training to be as short as possible in terms of getting you to speed on their projects. The other thing is in terms of communication abilities. I get a lot of complaints from the industry as their employers in terms of taking students know a lot, but when they are supposed to convey it, it becomes a little difficult. So the whole idea of not making this an individual project but a team effort was like the way the industry works. The industry works in teams because these are highly complicated problems, except for home built aircrafts, etc., which individuals can do also, or aero modeling, etc. But when you are in the industry, you work in teams, and it's very important to coordinate within the team and coordinate across teams. Like the aerodynamics team will coordinate with the structures team, etc. So you want that coordination to come in. So all these aspects is what I thought flight mechanics is a great course to kind of build up. In fact, I never even had this idea of these presentations until I think in the first or second class, I asked a question, how many of you are from an aerospace undergraduate background? And I saw more than half the class lifting their hands up. So rather than go into, again, a lot of things that many of you with aerospace background have learned, I want you to learn from each other. Most of the teams have a mix of aerospace and non-aerospace background. So the non-aerospace backgrounds is a great opportunity for you to learn from the others, to discuss what you are presenting and ensure that there's no duplication of efforts and there's a logical flow. To be fair, I think your team in particular, but also some of the teams which have already presented and also in the first presentation did a reasonably good job at that. But there's always room for improvement. And that's why we have these 13 presentations and only 6 out of them will be eventually graded. So the whole idea is there's a lot of room for you to improve and make yourself better, though there are different questions in terms of how you actually approach the whole idea. Okay. So this focused thinking is extremely important. Again, that's something that I tend to hear from a lot of the employers of our alumni, is in terms of they know so much that they tend to go off on a divergence, start talking about too many other things, which are all true, but may not be directly relevant to the question or may have a secondary, tertiary kind of an impact on the specific issue that they're trying to resolve at that point. So getting focused is very important. To have a broad base is very important to gather that information. The other reason why I'm going for this unique way of evaluating is that these days, of course, for the last at least 2 years, we have a lot of these AI tools. So going with homeworks or projects and things like that, at the end of the day, doesn't really lead to a good evaluation, as I've found from my own experience of teaching other courses. Here's an opportunity. You have to leverage those tools. It's not that if you use it, then your intelligence gets blunt or whatever. You have to use whatever is the current state of the art tool, because the people in the industry also get to use it, right? But it's a question of whether you're able to interpret that appropriately or not. And that will come out only when you're you're having an oral talk where you're actually trying to explain whatever information you have gathered. Information is not a problem at all. In fact, information overload is the problem today. So from that information overload, how you're trying to minimize that and get it focused to what is required to be answered, that's where the key is. So I'm really happy that you're trying to source from so many different things. I see some lecture notes and other things, also from the literature, both papers I saw the last time when you presented, for example, also in terms of the wide range of books that you're covering. I'm sure you're already doing it, but I would also encourage you to use a lot of these AI tools as well and try to see if that kind of helps you get focused a little more on the specific problem. Okay, then of course eventually you're going to interpret it, so absolutely no problem about that. Yes, it's good to have a lot of these equations and other things, because at the end of the day we are engineers, but I don't expect you to know the derivations of these equations, but at least in terms of the interpretation of the various variables that are used, various constants that are used, what is its physical meaning. So once you understand the physics, remember that however good we might be at our math, the math is essentially a tool to model that physics and then take decisions or improve designs or whatever you want to do or whatever role you're playing in the industry. Keep all of that in mind. Don't just think of that as just one exercise which is separated out from the rest of the course or rest of your MTech degree. This is a unique course in which everything comes into play. All the different things that you've learned, especially in the first semester and beyond, comes into play, and try to utilize this opportunity to bring together. So if you understand this intention from which we three have come, and they have put in a lot of effort in terms of arriving at these questions and coming with the subtopics, getting it verified by me, so that we ensure that what is being covered in the lectures and this kind of complements each other. Okay, so many of the things that you are talking about, I will be actually covering in my lectures later on, and may even look much simpler than what more advanced topics that you have covered or tried to touch upon. But the idea is that now you are familiar with a lot of this terminology, with these concepts, and I want you to then see from that perspective the basics. When you look at the basics, then how it built up the things that you already know, okay, in terms of terminology, jargon, as he mentioned. So I think that's where the key is. I hope it's very clear as to the purpose of this whole exercise, and just don't think of it as something related to this course or MTech, but even for your careers, I think this is going to be of great significance. So please cooperate and take in the right spirit whatever our group captain has mentioned right at the beginning, because all of that, for example, maintaining the discipline, decorum, silence, etc. It's okay when I'm talking and I'm lecturing. I've had a similar thing that many of you have been talking. I don't care, I don't mind, because for me teaching is the best way to learn, and I enjoy my teaching. And even if everybody's talking, or I don't even have a single student in the class, it's okay, I can continue lecturing because I enjoy, because while I talk I learn more. But when your peers, when your classmates are talking, they have put in effort, and it holds for everybody, of course. Just respect that time, energy, effort that they have invested in to arrive at a particular presentation, and I'm sure the presentations are going to become better and better. I already see in terms of the overall quality from these 4 presentations on an average compared to the first 6 presentations for the first question, there is some improvement. I'm sure by the time we go to the 13th question, there'll be an amazing level of improvement, both in terms of the content as well as the delivery. That's the reason why I would request all of you once again. I'm not saying don't speak. Speak if it's very important and absolutely essential and something that needs to be conveyed at that point in time, and speak in as low a volume as you can, you whisper, but do not disturb the entire class, and especially the people who are speaking at that point in time. Thank you. We will continue with the next team. If you want to add.
Just want to not add, sir. Firstly, you have presented an excellent presentation in my personal view. It is really a good job done. The simulations were really good. It is just that some few words were here and there. I'll show you what a Phugoid is in my own way, and I will show you the spiral divergence of this aircraft only. But as a whole presentation, excellent job done. Really, congratulations. Next team, please. Yeah. See, you get a yaw disturbance, right? Let's say it is the left. Now you will have a roll. You will have a roll down action. Then there is an increase in the angle of attack in this direction. Therefore, it try to, as it's moving forward, it try to do this. So it is a 3-dimensional like this. It is actually, if you see a paper now, it does this. Okay. Now you add the forward motion also into it. It goes this way and goes this way. Let us let's go first. Am I right, sir? Spiral divergence is like a tight spin. It goes into this, like screwing down. Goes into this and goes to the ground. And camel ride is this. Typically, camel ride is very neatly observable when you sit in an aircraft, especially when the gust hits. You throw it thrown up and then you do this. It's a camel ride.
Like sometimes continuous speed breaker used to come in also.
Yeah. So, I mean, and there are typically, first of all, it is very difficult. In fact, in I had the opportunity to take the last flight mechanics course, and we were all thinking if a spiral divergence is given the class to derive, how will we at all derive in the examination? Because a closed loop formulation, solution is not existent for a given set of equations. You will have to linearize, assume, and come down to 3 by 3, and then you get into an eigenvalue. So,
What about Phugoids and how? Because Phugoid is something like a roller coaster ride.
no, that is camel ride.
No, Phugoid is also something like that.
No, but when you sit in the aircraft, you can feel that you are doing this.
So that is a Dutch roll.
That's a Dutch roll.
Yeah, Phugoid is like a roller coaster. So it's like kinetic energy.
No, I think I like to physically see. As I said, I remember these two, but others, as again, I will have to really see the book and then I will also recollect. Immediately I remember, at this current moment, I remember these two. So,
You're right. Phugoid is essentially in the longitudinal plane, so there's no rolling or drawing that is involved. The name itself is a beautiful suggestion of what it is. So you see, Phugoid actually comes from a Greek word. You see, a lot of these things very interesting. We always divide left hemisphere of the brain, right hemisphere of the brain for science and art and things like that. All of that has been disproven. There's always an interaction between these. A lot of things technically you can learn from the very etymology. For example, Lancaster, many people consider him as the father of aerodynamics. He coined this particular term, Phugoid, because his Greek was not really good. He thought phug essentially means flight. And it's true. And oid is just a suffix to saying extension of that, right? Now, phug as flight actually means flight like in the sense of getting scared of something and running away. Let's say fugitive is another word. Somebody who's trying to escape from the law and from the police force, let's say. That kind of flight is what the Greek actually referred to as phug. Later on, he tried to correct it, but it stayed on. Nonetheless, the point is well taken that because you contrasting that with the other main dynamic instability that is involved, which is the short period oscillation, right? So from there, you clearly know that I think the previous thing really clearly mentioned that the short period and then you have, the other has to be the long period, okay? So then short period is essentially associated with smaller periods and therefore higher frequency and vice versa for the other, so, right? So therefore, your Phugoid, you're talking of long period and which is larger time periods and therefore smaller frequency. And which is why Phugoid is something that is experienced a little more because the short period oscillation is usually very highly damped. You saw some numbers for the eigenvalues of A, the real part of that in the previous presentation. I think that was really beautifully conveyed if we know the correlation between the physics and the math. You're essentially interchanging between the kinetic energy and the potential energy of the system, right? So the kinetic energy is reflecting itself in terms of the speed, essentially, because not so much of a change in the density, essentially. You're looking at predominantly the change in speed, which is contributing to the change in kinetic energy. Similarly, in terms of the potential energy, it's mainly because of the altitude change that is there. So essentially, it's an interchange which is happening. And because it's happening over a longer period of time and it's not damped out that easily as compared to an SPO, people actually experience it. Not only the pilots, the passengers also. You get that stomach upset kind of a feeling, right? Many of you might have experienced it if you had an inexperienced pilot, because most of these commercial passenger aircraft, a lot of thought gone into designing these numbers of the eigenvalues of A in order to make sure that they are within the reasonable limits. And if they don't, then of course the FAA or whoever the certifying agency is waiting to ensure that they do. It's happening in the longitudinal plane, means only 3 variables are involved. There are 2 translations and 1 rotation. And that rotation they're talking about is the pitch, right? And which is why you saw many of their derivatives also was not only with respect to alpha, but also like what we discussed already, CM alpha, for example, but also a CMQ. CMQ is the derivative of the pitching moment coefficient with respect to the pitch rate. You're bringing in that aspect also because the vibrating effect is having that frequency as well as the damping that is involved. So how you kind of balance these out is very important. But what is even more significant from these questions or whatever they presented is in terms of the takeaway of all of those things for performance, which is, I think, a little more effort could have gone probably in the previous team in terms of trying to, as I think he rightly pointed out already, in terms of the carryover. But I can also see the difficulty involved because many of these concepts itself you don't know. Then how to translate that concept into a performance, it takes a little more time. So it was reasonable for at least the first two questions to have longer durations of time. Really, left to me alone, I would not mind free time for all the questions, because for me, time is not as important, especially in this order of magnitude that we are looking at. Because typically, when you're trying to resolve an issue or a problem, you do get ample time. Of course, in terms of an overall development time for the industry, in terms of the aircraft getting to the market and all, you want to speed up because you don't want your competitor to get with a similar kind of an aircraft earlier. Like, for example, what happened with the Dreamliner 787 and the A350, right? So they might start sometimes at the same time, but one ends up much later. So time in that longer sense is very important. But in terms of addressing very focused minor issues, I think a lot more time has to be given. But here, because we have decided, we will go with the remaining questions only 10 minutes. I would suggest them a leeway of maybe 10 to 15 minutes.
Okay.
So,
plus 15 minutes plus
5 questions is acceptable. Beyond 15 is not acceptable. You'll be brought down the dais, right? 10 is ideal. Try to stick to it. If for some reason it exceeds a little bit to 15 minutes, that's fine. Okay, thank you.
Please, I'm extremely sorry. I would beg a pardon from the team if you have been made a representation of what the others were required. I hope you understood what I'm saying. You were in the stage. I am telling the weaknesses. So don't think that it was weakness representation of your team. No. I didn't mean your team's weakness. I meant the class to come up with those expectations. Your presentation per se was really good. You had some case studies. Well appreciated.
Sir, can we start?
Yeah.
Sir. Good afternoon, everyone. We are from Team Blackbird, and today we'll be presenting on effects of center of gravity on stability and performance of an aircraft. So ideally, we should have presented this earlier itself. We should have volunteered to presenting this earlier, because after all the complex presentations, both this class and the previous class, whatever the introduction I'm about to give might seem very basic. But as someone
Don't worry, you'll be in the same dilemma as me, because I'll be teaching some very simple aspects compared to what all you have been talking later on. So it's okay.
But as someone from non-aerospace background, even these basic concepts seemed rocket science to me like 1 week ago. So I think I would like to start with some basic definitions that all the other teams have already beautifully covered in detail. So the first one is longitudinal static stability. It's the tendency of the aircraft to return back to its original angle of attack after a small disturbance in pitch. And regarding how it does this by producing a restoring moment. And as we all know, in order to produce a moment, we require forces separated by distance. And the forces that we consider in this case are weight, the lift acting on the wings, and the tail down force acting on the horizontal stabilizer. We do notice that one of the forces that I mentioned here is the weight. And as we all know, the center of gravity is the point at which the entire weight of the aircraft might be considered to act. So the position of CG obviously plays a very important role in the stability of the aircraft itself. So coming to another term that's very important while discussing longitudinal static stability is the neutral point. Neutral point is essentially a design parameter. It is a point in the longitudinal axis, and if aircraft has a CG before the neutral point, it's considered to be stable. Whereas at the neutral point, it's neutrally stable, and beyond the neutral point, it's considered to be unstable. So yeah, I had already mentioned that the neutral point and the position of CG somehow affect the stability, and static margin is a non-dimensional number which basically tells us whether aircraft is stable, statically stable, neutrally stable, or unstable. So again, as I previously mentioned, that any point, if the CG is in front of the neutral point, it's considered to be stable. And in the flight manual itself, there are CG limits, which basically tell us up to which limits what is the range in the longitudinal axis in which the CG can be present. So we have the forward CG limit and the aft CG limit, and ideally both of these would be in front of the neutral point itself. So again, as I previously mentioned, we require a restoring moment for in order to bring back the angle of attack to its original value. So here we study the graph between the coefficient of moment and the angle of attack. And I've mentioned 5 CG points here and the corresponding plot lines. So yes, again, we notice that in case of intuitively we'll be able to understand that if the angle of attack increases, the restoring torque must be in the opposite direction, so that it brings it back to the original angle of attack. So we can intuitively understand that the slope of the this graph should be negative in order for it to be stable. So this is what we have tried to represent mathematically as well. I would like to have a disclaimer that we do not essentially, we are not trying to derive this equation, but from the equation of CM, which includes the effects of weight, lift, and the tail down force, we are trying to basically find the equation of CM versus alpha graph, which comes out to be a straight line as we see in this equation. And yeah, with that, I would like to conclude with the conditions of static longitudinal stability, where the slope of the graph should be negative, and the CM naught, which is the coefficient of moment at zero angle of attack, to be positive in order for the aircraft to be longitudinally stable. So
So good afternoon, I'm Meryl. So I'm going to talk about the CG envelope. So considering the course of a flight, the weight of an aircraft doesn't remains the same at all places of the flight. While flying in flight, the fuel is burnt, which causes a change in the weight as well as the CG position of the aircraft. So tracking this CG position while the aircraft is in flight is a very crucial aspect to maintain the safety as well as stability and performance of the aircraft. So in order to maintain that, the aircraft manufacturer itself comes up with a CG envelope that limits the movement of CG mostly along the longitudinal axis from a reference datum beyond which the CG movement should be restricted. So the reference datum is selected by the aircraft manufacturer itself. So let's say Airbus, if they choose some point as reference along the longitudinal axis, along which from which the CG position is calculated. So keeping the CG within the operational envelope is must for safe flight. So based on the CG position, the performance characteristics varies as well as the stability. So for maintaining a stable flight, the CG should be mostly at the forward of the CP, and the takeoff performance and the landing performance is calculated based on the most forward CG position, that is the most stable flight. So if it is the CG position is more forward than that, the performance will be lower than the calculated one. So both the CG position and the safe envelope tends to vary along the all phases of the flight. So the manufacturer itself, so we know that how to find a CG of an aircraft. It's like taking the weight of different components, multiplying the arm length from a reference point and dividing by the weight, corresponding weight of each of the component, we get the CG location from that particular reference datum. So the manufacturer also provides information facilitating the calculation of moments for fuel loads, which varies, which is a primary reason, I would say, for the variation of CG. Also, in a commercial aircraft, you might be noticing that people might be going for restrooms, and the flight attendant might be come with a push cart to serve you. So these all parameters cause a slight change in the CG as well. So they must be properly accounted as well. And so for your information, on an A320, which is this aircraft, you can see on the background. So the maximum distance along which the CG position may vary is 1.3 meter. And then as that of an A380, which is a wide body, this is a narrow body. So an A380, which is from its name itself, we get it, it's like a 80 meter long aircraft, but the CG position, it varies, it's like 1.97 meters, which is of 3% of that 80 meter. So this graph is a particular graph for a Cessna 172 aircraft, and I took that from the Cessna flight manual, and we can see that the x-axis marks the CG location of an aircraft. This is the reference datum, and this box corresponds to the
safe flight, and the y-axis corresponds to the maximum weight that corresponds to a particular CG location. Thus, a CG envelope can be said as a predetermined safe flight operation range of CG and the weight of an aircraft corresponding to the different phases of flight. So, it is always advised to operate the aircraft within the prescribed range to ensure safe flight all the time. So, the CG preference for the aircrafts like fighter aircraft and commercial aircraft vary with respect to their requirements. So, we know that for an fighter aircraft, maneuverability, agility, and combat performance is of the main importance. And whereas coming to the commercial aircraft, stability, safety, and efficiency. So, considering this, considering strong maneuverability, the CG location is preferred aft of the neutral point, and for that of a commercial aircraft, CG location is preferred ahead of the neutral point, that is positive static margin. And since this CG location is aft of the neutral point, we are from the previous explanation we got to know that it is like a negative static margin and negatively stable aircraft. So fly-by-wire technology comes into picture to compensate for that. So that is a Sue Felon for your information, and it's A350,000. So over to Vishnu. Oh, sorry, Alvin.
So now I'll talk about effect of forward CG on performance. So all these information, there is no explicit formula for CG and relating performance. So we tried based on our understanding, we tried to relate something with performance. So let me start from the takeoff. So if I draw DCM as a CL graph, this will be my neutrally stable point, and then if my if my CG moves towards the nose of an aircraft, let's take I want to trim my aircraft at this CL. If my CG is very far towards a nose, my aircraft will generate at this much amount of CM node. CM compared to the CG2, which is quite less. So based on this, if I want to take off where the CL will be lesser than CL max during a takeoff, I need to generate enough aerodynamic force on the elevator in order to pitch my aircraft up, which intuitively we can think that I need to travel further distance, which means so that I can get enough velocity. So thereby my takeoff distance will increase. And also this forward CG effect in practical case, if you think means either the tail load has to be reduced, or I'll be dumping more baggages near the nose region. Thereby, my nose landing gear will carry a heavy load. So this is like a formula that we get from the textbook. So this is the ground roll distance, which you can see that when the aircraft has to pitch up, the elevator has to generate a downward force. And this downward force will be added up to the weight. Thereby, the takeoff distance will, since the takeoff distance is directly proportional to weight, my takeoff distance will also increase. And also, I would say like the stall speed is also directly proportional to square root of weight. So when my weight increases, my stall speed will increase. And the liftoff velocity is 1.1 times of stall speed. Thereby, my ground roll distance will also increase. So in this way also I can relate that my ground roll distance will increase if my CG is towards the nose of an aircraft. It's very far. And higher stall speed and good stall recovery is that the inherent tendency of an aircraft is that when it is forward CG, it is more stable, so it will not allow the aircraft to pitch up further. So it always try to pitch down, so it has good stall characteristics. So and then if you look at elevator heaviness, This is an elevator deflection angle, and this is CL trim. So this is the equation for elevator. So this delta E naught is minus Cm naught divided by Cm delta E. Cm delta E is an elevator control power, which tells that how much the Cm will be generated when elevator is deflected. And d delta E by dCl is nothing but minus of dCm by dCl divided by Cm delta E. This term is negative, and this is for stability we need to be negative. So this is nothing but a static margin. When my CG is far near to the nose, my static margin is more, and my slope is also be higher, which means I also need a higher elevated deflection in order to trim my aircraft. So this is for forward CG. If you look at this point and CG1 and CG2 and CG3. So if I want to trim my aircraft at a particular CL, if it is in a CG3 point, which is very close to neutral point, I may need only a less deflection, and if it is CG1, I need a more amount of deflection. Elevated deflection will be higher. This elevated deflection is not something free. Even typical aircraft will have maximum elevated deflection of plus or minus 20 to 25 degree. That's what I read from some reference. Yeah, this is the equation that I mentioned. And so as I already mentioned that my weight of an aircraft, the tail downforce created by the elevator will add to the weight. So in order to lift the in order to maintain a steady level flight, my aircraft has to generate an additional amount of lift, which is the downforce. So to so my aircraft has to generate a force in order to overcome this downforce. So which will increase the CL of an aircraft, which also increases an induced drag. Thereby my drag will also increase. And in the case of T-tail and when downforce will, and also if we have when I deflect my elevator downward, so there will be downforce and there will be a component along the free stream. It will also account for the drag, which is called as a trim drag. So in the case of an T-tail aircraft, it may undergo a deep stall since I have to fly at a higher angle of attack in order to trim my aircraft. So if my tail is at the top, so I can this wing wake will not affect the tail. So I may tend to deflect my elevator further. So this will so I may go to a higher angle of attack, and then the entire wake from this will cover the elevator. Thereby the elevator will not be affected. So it will not give a sense like if we have a tail at the bottom, so the initial wake will affect the elevator, and it will cause as an aerodynamic buffet, which serves as an indication for stall, so that the pilot will account those things. But in the case of an T-tail configuration, it is very difficult because this wake will not affect this thing. So pilot may tend to pitch up further, so it may lead to deep stall. And so as I also said, like my drag will increase my power. In order to maintain a steady level flight, I have to increase my thrust. So my fuel thrust will increases, which also says that my fuel consumption will also increase. And so if I look at the power and thrust required as a thrust available curve. Okay. So this is my optimum value, which is corresponds to CL by CD max. So I may not be able to fly my aircraft at this point. I have to since my drag is higher, I need to fly. I'll be flying at this point. So which tend to feel like it made me to feel that the fuel consumption will also increase in this case.
And cruise ranges depends on LYD. My drag will be higher. So based on that, I can say that it is inversely proportional.
Sir,
It will affect the density. It will affect the range.
Okay. The two teams take 2 hours.
And
Okay. I can take like quickly, but if they finish.
No, we will have it. The starting of one. Don't worry.
so if we look at the rate of climb equation, so it's nothing but thrust time velocity minus drag into velocity by weight. As I already mentioned, the weight will be goes higher and the drag is also higher. My rate of climb will decrease. So for if I have forward CG, my starting margin is more, then the rate of climb will also go more. It will reduce. So which means that I cannot climb at a higher altitude. Let's take my design cruise is around 33,000 feet. So with the forward CG, I cannot go. I cannot cruise at this speed. I'll be traveling at a lower altitude. Let's take it as in 30,000 feet. My density will be higher compared to this. My drag will also increases in this sense also. And it will also affect the range and all other things. And yeah, so also I can look from the power available and power required curve, because the power available with respect to altitude, it will decrease. This is at some altitude. This is my power required curve. And my power available curve with respect to altitude, it just go higher, and my power available curve will drops. Thereby my excess thrust is dropped. It's also it also make the rate of climb to decrease. I can also say from in this sense also. So now if we come to pull up and level turn maneuver. So for these two maneuver, my lift has to be higher than the weight, which means my load factor is greater than 1. To maintain a level flight in this, the stall speed, if you took at stall speed, it will be square root of n compared to the stall speed of level flight. So my even in a level flight, the stall speed is increasing because of forward CG. For maneuvering flight, it will further increase by the factor of root n. And my elevated deflection will also increase because so if I pitch my aircraft up, my tail will go down and it will see some effective velocity from here, and this will increase an angle of attack. And if I consider an hinge point here and my CP is over here, this will further deflect down and it makes a tail, it will further, this will create a nose down moment and my elevator will keep deflecting up. So already we have, in order to maintain a steady level flight, I will be giving an elevated up deflection, and if we do maneuver, it will further deflect down. So it will deflect by the amount of Q times LT. LT is momentum distance from the tail aerodynamic center to the CG point. Sure. And Q is nothing but the pitch state, which is velocity by R. And tau is nothing but the flap effectiveness parameter, which is d delta E by d alpha t. D alpha t by d delta. It depends on the tail area and the tail area and by the wing area. So now if we come to landing part, the flaring will be very difficult because it will tend to, it cannot, when the aircraft comes to land, it will always tries to land with the main landing gear. But since the CG is forward, it tends to land with the nose landing
Who has
gear.
4 o'clock class can leave.
Next class, then in that case, lottery will have to happen in the next class.
Oh, okay.
Can one of your reps remain of your teams? We will have lottery of the picks of the next presentations. So one rep is okay, just to pick.
Yeah, you can catch.
So during a landing, the nose landing, there is more high tendency for the nose landing gear to touch down. Since these landing gears are not designed to carry a much weight, and it may lead to structural failure. And also, as I mentioned, whatever the reason for increasing takeoff distance, it also increases the landing distance. That same reason holds. Because for landing, the velocity for landing will be around 1.2 to 1.3 times our stall velocity. So it will also lead to increase in the landing distance. Now, if you consider the case where the landing strip or takeoff aircraft is around higher altitude, which when density is low, the takeoff distance typically will increase. If with the forward CG, it will increase further. So one should consider all these things with the forward CG. So next, Vishal will explain about the effect on aft CG.
Hi, I will be presenting the effect of aft CG on aircraft performance. Earlier, you could have heard him saying we need a large force from the horizontal stabilizer. Let's see why. When the CG position is very forward, this distance is very high. So the moment required to stabilize the aircraft from the horizontal stabilizer is high. So we need a large force from it. But in case of aft CG, we require just a small force. So this is a very important point to understand the performance. When we require a smaller force, it means every aerodynamic force is related with a drag, like induced drag. So when we require a small force, the drag is less. So which eventually lead to better fuel efficiency and increased range. And let's see the effect of CG on the rate of climb. Rate of climb is just dh by dt. If people from bachelors would have been aware of this formula, rate of climb is equal to del p by w. Del p is just excess power. You could have seen in movie, whenever we need to climb up, they increase the thrust, which essentially increases this del p. So we have already established the fact that in aft CG the drag is less. So it essentially means that the power required is less. So we have excess power for rate of climb. So we have a higher rate of climb. And the effect on stability. Earlier here, you have seen the graph multiple times, CM versus alpha. When the CG goes back, the slope becomes even more negative, leading to, the slope becomes positive, leading to lesser stability. Lesser stability naturally means more maneuverability. So since the aircraft is less stable, the spin recovery characteristics in this case is bad. And let's see the effect of aft CG on minimum control speed. Before, maybe I have to explain what is minimum control speed. Just imagine yourself seeing the aircraft from a top view. When one engine fails, it's known as a one engine inoperable condition. Let's consider the one engine on the right side fails. Then we have a thrust asymmetry. The flight will yaw towards the right then due to moment. Let's consider CG to be here. Then how do you think we can bring the flight back to its original position? We will use the rudder. So basically, to bring it back to the position, we need a aerodynamic force from the rudder. This force is directly proportional to this force, whatever the force may be, is directly proportional to the square of velocity. So to get the required moment to bring the aircraft to its original position, we need a considerable force. That means there's a minimum velocity that's needed to produce this force. That is the minimum control speed. But when we shift the But when the CG goes aft, this arm length reduces, which essentially means that the moment, the restoring moment is nothing but this R into B. When the B reduces, we need a greater R, and the R is directly proportional to square root of V. So we need a higher V. V is the minimum control speed. And just to summarize, so the aft CG is less stable, and it is more fuel efficient, increased range and lower stall speed, and it has increased minimum control speed and increased rate of climb, and it has a bad stall recovery characteristics. Thank you.
Now I will tell about some real case accidents that happened due to the CG shift. Douglas D8 is one of the famous accident that occurred due to CG shift. it was scheduled to go from Miami to San Diego on, you can see the date, August 7, 1977. As soon as the takeoff happened, the flight took a sharp pitch-up movement, and it reached altitude of 600 meter, and it had a pitch-up altitude of 70 degree, and which eventually lead to stall and the crashing of the aircraft. Before going to details, let us see a video of how it actually happened. As we can see, the aircraft went to the stall and it eventually crashed in this. So let's see what actually happened during that. Initially, the aircraft that was scheduled there was N30 UA, but due to some condition, the aircraft got delayed, and as a substitute, the airline has given Air 27 UA for. So, okay. So as a substitute, they gave Air N27 UA for the airline. But initially the instruction was given for the N30 as like the payload condition was around 88,000 pounds, and for it was given for a 30% mean aircraft mean aerodynamic center, and in the panels which I have shown, it was instructed to keep the second and 17th position as a empty space so that the CG location will be in the correct as required. But as the aircraft changes to N27 UA, it was required to keep the 13th and 17th position empty, and to take the payload in the 13th position to the 17th and keep it. And it also required for N27, the new aircraft, to have the reduce 1,000 pounds from the 10th position of the pilots. But it was not confirmed that the supervisors who was taking in charge of the payload to got the new instruction, and it was determined that the old instruction was made in the new aircraft. Also, it was been noted that you can see the palace location. So this was I am telling about. And it was also came to note down that they didn't include the payload weight of the nets, covering and other stuff, which itself came around like 4,400 pounds. So due to this, all the things together, the CG location has shifted from the original 30% of a main aircraft to it went to aft location, it went to aft of 33% of the aft limit. Due to this and the trim condition, which is initially meant for a forward location, as soon as the airplane take off, it experienced a sudden pitch-up movement, which the pilot couldn't immediately react to it, and which eventually lead to stall and the crashing of the airplane. Next aircraft we will see about is the DS3 3 turbo otter. This is a cargo plane which was loaded in IISc, where they didn't weigh down the payload weight, and they didn't have any document for the weight and balance calculation. And after it went to Soldanta to pick up around 9 passengers and the baggage of those passengers. What the pilot did was he did the weight and calculation, but he did it with the information that he got from the passengers, which was not as accurate as it was meant to be. And also for the cargo, he got the information from the company which he hired him to carry the payload, which the company gave him around like 300 pounds estimated, but the actual payload was calculated to around be 800 pounds. So due to this, and I have to note that the payload was kept in the aft location of the airplane. As due to this all, the CG location has significantly went to the aft location, and even if the pilot did a full nose down movement, he couldn't bring back the airplane to the original condition, and which eventually lead to the crashing of the airplane. There was nobody got killed in this, but they got severely injured in this accident. These are the other accidents that occur due to CG shiftings, and finally, we know the importance of the as my teammates have said, the importance of the forward and CG location. We can show you the how important is to manage your CG. So it's always important to keep it in the CV envelope, as Elil said, which can be found in the booklet the pilots has. And also it is important to note down the payload locations, like where the payloads are being kept and the weightage of the payloads. And also we have to take in mind of that the fuel decrease as the cruising, and that will eventually lead to change in the CG locations. So, and it also the airplane loader should know the importance of the errors in airplane loading. These are the small steps we have to take care so that no more accidents and will take place in the future. And I have to finally say that CG management is not just for performance; it's also meant to be for safety. So CG management should be a prerequisite for every airplane. Thank you.
Questions from the audience, remaining audience? Start.
Nothing, sir. I've got nothing. I think.
Okay, I think they're satisfied. Yeah.
Good.
One more team they will present on Monday because they have a class at 4 o'clock.
Good afternoon, everyone. My name is Ravi Agrawal, and we are the members of Team ArchAngel A12. So we will take a slight detour. So we will talk about the effect of tail on the aircraft performance. And since in this theme, a lot of teams has already delved into stability and a lot of its derivations. So we'll try to focus more on the performance aspects of the effect of tail. So the first question is why the tail is required.
There's no time limit for this question, so you can feel free to take as much time. So only for the next question that you're answering.
Yes. So the primary question is why the tail is required. So in general aircraft, the CG is in front of basically the lift force. So usually there is a pitch down movement, and to stabilize it, we need a tail which is trimmed to produce a restoring movement in general situations. So this is basically the primary work of the tail, and this is the movement balance equation. But since the aircraft is generating a negative lift, negative downward force, the lift is supposed to produce the wing is supposed to produce sufficient lift to counter the weight and the negative force generated by the tail. And since the wing is producing more lift, the CL square is increasing, which in turns lead to more induced drag. So basically, this leads to the fact that we are incorporating tail in the aircraft, which leads to more, which produces the need of producing more lift, which leads to more drag. And since in general aircrafts the tail corresponds to 3 to 6% of the overall empty weight, and if we basically if we make heavier tail, the CG shifts behind, and we need to shift the wing behind. And since the fuselage gets heavier, we need more fuel, and this is a cycle which tends to heavier takeoff weight. So this is a summary of things like since we are using higher tail volume, parasitic drag increases due to more wetted surface area, heavier tail structure which leads to more fuel tanks, higher takeoff weight, and higher induced drag due to more CL square. So overall, the tail leads to more reduced payload or range, or minimize the LYD ratio. So this is a cascading effect, and other previous teams has already delved into it, so we will not talk much about it. But since the tail leads to a negative slope of dCm upon d alpha, so it's a stable equilibrium, and the static margin defines the quantify the safety. And this is the tail volume formula, which basically defines like what we are trying to maximize, since there's a lot of performance parameters and different aircrafts are designed to maximize different performance criteria. So the VH plays a very vital role in defining like how the tail affects the performance and what we are maximizing. So this is a rough summary of how tail affects, like it increases the parasitic drag, it increases the structural weight, it increases fuel weight, it basically increases takeoff distance, fuel burn, climb performance, and other aspects. So this is a short summary of how the tail is affecting the performance parameters, and my other teammates will delve into how different types of tail and other performance parameters are getting affected.
Okay, good afternoon, sir. Good afternoon, everyone. So I will take it from here. I will talk about a little bit about how tail will affect dynamic stability. Like static stability is statically stabilizing, as well as the effect of tail, it is dynamically stabilizing as well. A larger tail will lead to higher damping, as we can see over here. Whereas a smaller tail, it will lead to low damping. So tail acts as an aerodynamic damper for pitch damping, and a larger tape increases our handling qualities. The second thing, the pitch damping is also like it is proportional to the square of the tail moment arc. So a larger tail moment arc will lead us to better stability in this region. Apart from that, uh, I will spend a little time on different types of dynamic modes. Like tail does not have much. There are two basically dynamic modes in the pitch. That is Phugoid and short period mode. Tail does not produce much damping in the Phugoid mode. It is mostly produced by the drag. Whereas in the short period mode, tail is the primary driver of damping. When it comes to lateral directional, we need instead of a horizontal tail like this, we need a vertical tail. Right, as we can see over here. That will give us the stability in the lateral direction region, because these two things are coupled, lateral and directional, both of them. And this, just like this will have a VH, this is the tail volume ratio for horizontal tail, this will have VV, and higher VV will lead to better stability, both static stability and dynamic stability for lateral direction region as well, lateral directional modes. And but it will, of course, it will lead to increase in weight and increase in drag, reduce lift. This is like holistic what will happen to the performance, right, if we take into account everything. Like Ravi has already introduced everything, so I will just skip this part. Then I will talk about a little bit of limitations of what we have done until now. This I will explain on the basis of some papers. So this was one research done in University of Naples, in which they found that our current understanding, like the way we predict the drag and lift on using classical linear theory, is very what do you say? It's very inaccurate. As you can see over there, they did a CFD analysis as well as a wind tunnel setup, and they found that, look at this. So this is the directional stability. This is body plus vertical tail, as per found by the CFD analysis. And this is the one which we can see by the one we can predict by natural classical methods. So you can see there's a huge error in between those two things, like almost a 15% error. So that will we'll need a bigger tail, like we'll need a 15% larger tail to counteract this. This is like the pressure distribution for beta equal to 5 degree, like side slip angle on a vertical tail. So this gives us one of our limitations of the linear theory, that it's not able to accurately predict how much the size of tail we require for really designing an aircraft. We actually need more advanced analysis, wind tunnel and CFD. Next, this is the one thing that I introduced in my last presentation as well, like how in VTOL and STOL aircrafts, they basically design the way that they design the propellers over the tail. So in order to stabilize the flow over the tail, this will help us this increases the effectiveness of the tail by 10 to 15% in power flight. Like this helps us to reduce the size of the tail, since it will not require that much. It increases dynamic pressure over the tail as well, and stability is increased for a smaller tail. Next, one of other limitations is based on, I will use this to explain the other limitations. It is basically compressibility. Like at higher Mach numbers, of course, our analysis will be completely inaccurate. As you can see over here, as the Mach number increases, the stability decreases for a tail, for a similar tail. And linear low speed theory actually it fails to predict the loss in directional stability. And this is all the reduction in as increase in Mach number. This is the reduction in tail effectiveness and our reduction in controllability as well. And so that is the reason when high speed aircrafts, they basically design the tail based on the worst case dynamic pressure condition in order to ensure. Because simple static margin and VH ratio won't be able to help us design tails. Next, I will talk about different tail configurations. As you can see over here, this is a conventional tail configuration, a vertical tail and a horizontal tail. This is a T-tail configuration, where horizontal tail is placed above the vertical tail. This is V-tail, and that is a cruciform tail. So generally, a conventional configuration will give us 0.9 to 1.1 tail volume coefficient, and it's standard. Suppose if we keep this as relative, like suppose this gives us 0, relative L by D. Using a T-tail configuration, the use of this is like it increases effectiveness for the tail. So we will require a smaller horizontal tail with T-tail configuration compared to conventional tail. But the problem with T-tail configuration is like it can induce a deep stall region, and in order to avoid that deep stall region, we need to actually have a very more advanced kind of control systems in order to avoid those deep stall going into that deep stall region. That is one of the limitations of this. So it can't be used on a high angle of attacks. Its positives are it will increase the effectiveness of the tail. Apart from that, this configuration isn't much used because of its stability hazards. Next, I will talk about a V-tail configuration. Basically, it uses instead of putting a horizontal tail and a vertical tail, basically we are putting a V-tail like this on the back of the aircraft. So for this kind of configuration, it allows us to have a very it allows us to combine the effects of both horizontal and vertical tail and reduce the size of the tail. It will also give us a higher L by D compared to normal conventional configurations, and stability at a lower weight of the tail. So smaller tails will lead us to better same stability that we need in conventional. But the problem with this one is like we need a better control system. So instead of an elevator and a rudder, we need a rudder wader kind of mixed configuration. So if this both goes down, then this will give us a pitch up. And in order for the yaw control, we need one up and one down. And apart from V-tail, we have a canard tail. It is even the first wRight flyer was canard configuration. And instead of producing a lift backwards, it's produced one forwards. this this reduces the main wing loading and the induced drag. But for this, it forces the main wing to operate below its maximum CL. So it increases stall speed doing that. And apart from this, this is the recently coming one, tailless configuration using a reflexed airfoil. But for this, it will give us the maximum maximum weighted area efficiency, maximum L by D, lowest drag possible. But the problem with this one is we need a very good very good control system, like a fly-by-wire control system, which is able to handle this one. So now will I ask my teammate Deep to introduce how we can design different aircrafts using our understanding of tails.
Good afternoon, everyone. So I am Deep, and I will be discussing about the different case studies. So designing the tail and in fact the aircraft also is an engineering optimization problem. So here we always want to maximize the parameters such as aerodynamic efficiency, the range of the aircraft, and the payload. So that's our main goal. But we also have our constraints. So the constraints are like, say, the stability margin must be greater than the minimum safety limit. The control authority of the surfaces must be able to handle the rotational requirement, and the structural limits of the aircraft must be greater than the loads which we are trying to design the aircraft for. And with respect to the aircraft tail, the variables which we want to work in for our designs are basically the tail area, the distance of the tail from the center of gravity, and the position of the center of gravity of the aircraft. And our optimal tail design will be the smallest one, so that we can reduce the drag margin that barely satisfies this constraints which are given here. So based on this, there can be different case studies based on the different design philosophies. For example, in the first case, which is our transport aircraft, we want safety to be the first priority, safety and smoothness of the flight. So accordingly, our stability margin is higher, around 10 to 15%. It should be positive, so that we can take advantage of the natural aerodynamic stability. The VH, or the tail volume coefficient, is approximately 1.05, but this comes with a cost. This stability comes at a cost, and the cost is basically we get increased drag due to which we need to burn more fuel. So that's taken as the cost for this stability. The next case is the fighter jet, where we are more concerned with the agility and the maneuverability. So in that case, we have the lowest tail coefficient, other than tailless designs, which I will come later on. So it's approximately 0.4. And for agility, we have our stability margin to be nearly 0 or even negative. So this helps us in agility, and also at higher Mach numbers when our aerodynamic center goes back. So there, this negative stability margin helps by increasing the stability there. But since at lower Mach numbers, at subsonic speeds, the stability margin is negative, for stability to take place, we need fly-by-wire systems. So now after this, I will talk about the extreme optimization for efficiencies. So the next one is the example of glider, where we want to fly as far as possible. So aerodynamic efficiency becomes the utmost importance. So in that case, we try to have a lower tail volume. So in this case, our strategy is to have extremely long momentum, which is basically the distance of the tail from the center of gravity, which allows for a tiny tail area and hence lower drag. And we get a resultant L by D ratio of greater than 50. And the final example is basically of the tailless design, which is used in the B-2 bombers, for example. So in that case, since there is no tail surface, so VH is equals to 0, the reflexed airfoils and split drag rudders, they act as the virtual tail here. And in this case, as I've already said, there is no trim drag or even interference drag due to the absence of tail, but it is again a unstable design, so it requires again fly-by-wire systems and such control systems. So I will talk a bit more on the tailless design once again. So because of this absence of this tail, there is no drag, as I've already said, and we achieve a L by D ratio of greater than 25. But again, since this is an unstable design, we require fly-by-wire systems and other computerized control systems so that the stability is maintained. So now the conclusion will be like handled by Anurag.
So I will just quickly conclude the presentation. Simply, basically, what are our limitations? Limitations are basically compressibility effects and the invalidity of linear theory in high velocity regions, as we see over there, and transonic effects. Apart from that, one more we have realized that our original the way our linear theory is not completely accurate when it comes to designing tails for aircrafts. We need more higher analysis like CFD and wind tunnel test. Apart from that, so concluding it, like we have our design constraints are two basically: a static margin and tail volume coefficient, and we have to ensure stability while but if we increase the stability, our drag will increase, weight will increase, and our CL max will decrease. So there is no optimum strategy when designing a tail. Our front, it is an optimization problem. We have to work within certain constraints, uh, and that is the reason. So, like this is a flight mission profile, as you can see over there. If we even if we increase the volume of the tail, we'll have a less aerodynamically efficient aircraft, but it'll take a higher takeoff range, and cruise endurance will also reduce. And this is the chain of performance cost, like how things go from like geometry will affect stability, that will affect our trim, that will affect lift distribution, and that will be our outcome when it comes to designing tail. You can. So this is the final slide I want to talk about. So as you can see here, this is the wRight flyer. It has like two wings, canard wings. This is our current flyer, and this we are moving towards. The one we are moving towards is basically kind of designs where we actually have no tails basically. So we'll have artificial stability, and that comes with increasing technology. That we have better control systems, we'll be able to actually handle such designs. Apart from that, there's a very famous quote. It says like, design is overrated and manufacturing is underrated. So even if we design a very good aircraft, at the end it depends whether we'll be able to manufacture it, we'll be able to like pass it, we'll be able to pass the maintenance criteria, we will be able to work for 1 year, 2 years, we'll pass the certification criteria. That thing also comes into the factors when we are looking into it. Other thing is cost as well when it comes to design. So we have to optimize all these things in order to make sure that is the designer's art, right? Finding the minimum tail volume to ensure the safety for the aircraft, and according to mission driven mission for that particular aircraft. Yeah, thank you.
Any questions from the audience?
So one question is, you mentioned about the crop was increasing the efficiency or the efficiency of the tail. But doesn't it also affect the stability? Stability in the sense it is weight. So if you keep a prop or if you keep a fence or let's say doesn't it make more complicated? Make it more complicated?
I mean, how will it make more complicated?
What do you mean by complicated? There is no uniform velocity coming in.
Okay.
It will have velocity of all the components.
Okay.
And the estimation of the velocity as well as, let's say, the natural frequency of the air coming in hitting the tail matches with the natural frequency as well. Then it can create cutovers.
Yeah.
And one more, that's why if you see, how many aircraft does use the technology?
I mean, the technology mostly used in STOL and VTOL aircrafts. So in those aircraft, the speed is not that high. So the cases of natural frequency matching or flutter will not occur.
Can you like give an example of any aircraft which uses the
I could explain STOLs and VTOLs.
Where are they? I have not seen that aircraft.
Okay, I mean, they are research topics. So, I mean, but STOLs and VTOLs generally use this kind of design. The primary thing is we have to ensure that the flow does not separate from the tail, right? Our primary concern is the flow separation. In order to prevent that, we put the propellers in front of the tail. So it will ensure that the flow remains.
But if you consider STOL, because such as B22 Osprey and such things, they don't use this technology.
I mean, you are giving a particular example of an aircraft which does not use that. So of course there are different designs. This is one of the designing.
That's what I'm asking. Like, have you seen any aircraft? Like, can you give any example of aircraft?
Okay, no, I don't have an example in my mouth. I'm all actually looking into that research paper, and that is what I was. Anything else? Okay.
Why does it happen?
And one more thing, adding on to her question. You also mentioned it is not used in practical cases. I think if I remember properly, you mentioned that TTL is not much used.
Yeah.
But if you see all the cargo aircraft, they use TTL.
Cargo aircraft, I generally use H-tail, not T-tail.
No, see C-17 Globemaster. That's okay.
Yeah, C-17 Globemaster.
Yeah, you see antennas, they have TTLs. I use cargo aircraft, they have TTLs.
But they don't have to go at a very high angle of attack, right? That is their deficiency. What T-tail does, it increases the weight and it reduces LYD and it increases effectiveness, right? Okay. That is what T-tail does, right? For cargo aircraft, you don't need a very high angle of attack, right? Yes. So actually, it is basically it is designed for that particular purpose for mission. Anything else? How it goes into deep stall, like at a higher angle of attacks. Yeah. So at higher angle of attacks, the flow separation becomes much easier with this kind of technique. That is using tenders like this one.
Sorry? No. I can answer the question.
Yeah.
So basically, the wake of the wing will cover the tail. Yeah, so that's it. No, the wake, see, that's what. See, the wake will go about the tail, and the detail will not have any effectiveness, and you will not get any control. Yeah. Yeah, that's, but you don't get that in high angle of attack. You get wave, but this is completely shadowing the vertical tail, the horizontal tail, which is at a higher position.
Generally, the tail is over here, right? Yeah. So the airflow over here will actually energize the flow over here. Right? Simple as that. But since the tail is over here, it becomes easier for the flow to separate. That is easy.
I'd like to congratulate you once again. I think I mentioned this after your first presentation also. I really like the slide designs in terms of minimalism. Also, you're giving the credit to whatever the AI tools that you obtained the results from. There are a few things also which I liked is in terms of the research papers and bringing their relevance to this. And also in terms of the various tail configurations that you covered. I want to appreciate that. One of the things that you mentioned throughout the talk is in terms of the volumes, the VH and VV. I'm not sure if I missed it, but did you define VH and VV?
Actually, not in the slides. I'm not defining.
Okay, do you know what it is? Yeah.
So only VH is defined in slides.
Okay, yeah.
So in slides, I have not defined vertical tail separate.
Okay, because it's very important to understand, because when we colloquially mention tail volume, a lot of people will think it's just the volume occupied by the tail, whereas the LT factor is very important to mention.
It is also related to the volume.
Exactly, and also in terms of the non-dimensionalization, how exactly it is done. Another thing is, if you look at, because you're a tail specialist as far as this particular question is concerned, I'd like you to loudly think around with me on this fact that for conventional designs, you of course talked about a lot of unconventional designs, but for conventional designs, we typically have two stabilizers, that is the horizontal stabilizer and vertical stabilizer. Okay, the horizontal stabilizer is essentially in the XY plane and the vertical stabilizer is in the XZ plane. Right? But the aircraft is a three-dimensional body and three planes are involved, right?
Yeah.
So just like three coordinates are involved, three planes are also involved. So what about the YZ plane, which is essentially along this span and downwards, right? In that plane, you do not have any surface. So what is the key over there? You would expect that if you have to have a stabilization in any particular direction or a plane, you are having a tail to do that, okay? A conventional design, of course, you have talked about tailless blended wing body and all that. But in a conventional design, why nobody has given ever a thought, or there has been no need for a stabilizer in the YZ plane?
One of the things is like the aircraft is symmetrical in the YZ plane first. And the second thing, the way aircraft is designed. So this is our plane, these are our wings, and this is our tail. So we want to basically stabilize it in three modes, right? Pitch, roll, and yaw. So pitch will be done by the vertical tail, right? It will stabilize the pitching movement. When it comes to yawing movements, the way it works is like the yaw and roll both are coupled. Like suppose we are rolling. If we roll like this, so we'll use the elevator, right? So in order to roll like this, we have to increase the lift over this. Lift is increased over here, lift is decreased over here. If that happens, what will happen is the aircraft will also start going.
Because let's not confuse between control and stability. Okay, so your control, for example, in the other two cases are with the elevator and the rudder, and here also you have a control with the aileron. Right? But what we are talking of is the stabilization. Okay, so stabilization is not about the rudder and the elevator, but about the vertical tail and the horizontal tail. But I'm asking, why not another tail like this? So if this is the aircraft in this direction, why not a tail? So you have a tail like this, a tail like this. Why not a tail like this?
Okay.
Just a trick question, but try to think aloud.
I mean,
see.
I mean, since lateral, I was actually explaining that lateral and actional are since coupled, right? The yawing and rolling motion are coupled in it. So a single vertical stabilizer would be enough to stabilize both of them. That was my answer. But Ravi will like to answer.
Also, like the same point, like they are coupled, so like we can use the other one to stabilize it, and also like it will increase the drag like significantly. So it's not preferred.
Okay, thank you. You can continue with the next question.
Yes. Thank you. The next one.
I don't know the other aircraft have a knob. I just want to tell you, 21 has a rudder. We call this as tail. I mean, vertical stabilizer. We have a rudder here. 21. That's a few. That's the model. Exactly like a fish. Yes. 21 has it. Most of the time, most of the aircraft don't have it. See, you want everything to be symmetric. No. See, this is symmetric. This is symmetric. Other than this portion. Rest are symmetric. But 21 has that also. Like missile.
So we have not prepared our that question.
No. It is just information.
No, it's not regarding that.
You do that
on next presentation. We are saying like we are not prepared that. So
okay, but don't have a